I'm also one speaker.
Okay, do you also want to check your presentation?
I want to take a look at whether my slides worked well.
Okay, let's give this see. Okay, what session are you speaking, sir? Do you know what session you are in?
Close to noon in the morning.
Let's see.
Yes, that's great. Thank you.
The last one in the morning.
Oh, there we see.
Yeah,
Number 5. Let's have a look.
Yeah, looks works.
That's the one you have to presenting, right?
Yeah. 6 to 9 ratio. Hi.
Yeah. Oh, it's quite a long presentation.
Okay, thank you. Wow,
You're welcome.
I will be quick.
When the AV guy is commenting.
Depends on the speed.
I have a different Zoom room for that.
Good morning.
Okay.
Do you have the details for that, or would you like me to give you the details for that?
Don't have it yet.
Okay.
I'll speak to.
So are we supposed to, what's with the
I'll speak
microphone
to-
thing?
Yeah.
We're supposed to.
Do you want a mic and I'm already? So you are speaker
Okay.
number 1.
Okay.
I can
I-
wait,
I-
I don't need to wear it the
Okay.
whole time.
Yeah, I emailed it
I'm
to
speaker
Chuck,
number 2.
otherwise I
Oh,
can-
there's the review and then there's me.
Otherwise, I can give it to you.
Yeah, so the
Okay.
first the review.
And then I also
Yeah.
have a present for all of you to share.
thank
These
you
are
very
stroke
much.
waffles, which are like the only thing worth exporting from the
Yeah, so
Netherlands
I
in
would
terms
say
of.
you can come up at 10 to
And I think there are enough that you can all have at least one, and then after that, you have to fight it out.
This is the second time we have it.
Very nice.
Okay. Sorry I'm beforehand.
You're welcome.
Yeah.
So you
And
also,
then for-
would you like to check a presentation?
Yes.
So you are number 4. We didn't receive a presentation for you.
I sent it this morning.
What you need to do?
Okay, could you repeat?
Oh yeah, I'm gonna give it to you. IAU Astronomy.
Should we wear the device or not?
Gift heel, present heel.
I'm assuming it'll take us a little bit of time to switch from, like at the lunch session, but not much. I'm presenting something, maybe someone else is presenting something at lunch. We'll just screen share in the Zoom. I think that's easiest. We don't have to upload anything. Yeah. Okay.
We're gonna wear
And
this
then
when
for
the
online
session
people,
begins,
I think
or
my
when-
idea, my assumption at least, is that if they just post things in the chat and we have someone to read it out, that's easier than like connecting them to the system audio. Okay, perfect. Thank you.
Okay. The battery is for 40 minutes.
Yeah, no, not the batteries.
No.
The presentation
President.
will be before you.
Before
will be
me.
about 14 minutes. So when that presentation starts, I would
Okay.
like you to come up with your microphone.
Okay, clear.
Moderate now. Oh yeah. And see, you had a question?
Yeah, I'm next speaker, I believe.
Are you the first speaker? Okay, perfect. You can mic up in the meantime. Yeah, you guys having a 50-minute talk.
Yeah.
No, I think we should hide it.
Yeah.
Just hide it in front of our eyes, yeah. Because we all gonna want it. I would really want to eat that, do we? Or we should do one round.
Just so you know, I think still, there is a live mic up here somewhere. You can kind of hear a little bit of stuff on the speaker down there. I don't know which one it might be. Yeah.
Yes, yes. Hello. Good morning, everyone. While people are still sitting in, there is 2 announcements. Yesterday, we a bit relaxed and forgot to introduce ourselves before we ask questions. So they're on Slack and Zoom, people were asking, oh, who asked that question? I would like to follow up with that person. So please don't forget to say your name, which university institute you're from, so people can connect with you and have a good chat. And also our wonderful support team reminded me that if you know that you are the next speaker, please go upstairs in advance so your mic is being set during, for example, question session. And so we are not delayed any further. It's my biggest pleasure to introduce our first review speaker, Céline Peroux, who will tell us more about connecting H1 to multi-phase ASM at all redshifts. So we're very excited. Thank you, Céline.
Good morning, everyone. Hi, my name is Céline Peroux. I work at the European Southern Observatory near Munich in Germany. And I'm going, thank you, to tell you a bit about H1 and the connection with where am I going to move the slides from? Is there a pointer / moving slides tool? It's coming. Ah, you do that, Antonio? Okay, good. So I'm an instrument scientist at ESO. That means that I work on the building of new instruments. I have in charge 3 projects, NIRPS on the left, which is an instrument that measures the radial velocity of exoplanets in the infrared. We've put it on the telescope a year ago. We are working on Blue MUSE, which is a blue extension of the MUSE instrument, the VLT, Very Large Telescope. I'm working on NDS, which is a high-resolution spectrograph that is going to go on the extremely large telescope. But today, I would like to tell you, Antonio, next slide, about why I love H1. Thank you so much. Thanks. I think it's important that as a community, we keep conveying that message, which is, of course, many of the universe constituents are very poorly constrained. We don't know dark energy is made of. We don't know very much about dark matter either. But even the normal matter, the baryonic matter, is poorly understood. So only 10% of the baryons emit lights in stars that would populate our galaxies. The remaining 90% of the baryons are all also poorly constrained because they are very difficult to observe. And why that? Is because it's in the form of gas, right? So the gas, I'm going now to talk about in more, trying to put into context of the cosmic time evolution of these different phases of the gas. So H1, we've heard, has been very successfully probed at low redshift using essentially 21 centimeter emission. And I'm going to, again, argue that we have a lot of information about H1 at high redshift from a very different technique. This technique is quasar absorption spectroscopy. So what we do here is we use an unrelated bright background source, such as a quasar, to study in absorption along the line of sight all of the H1 gas that is being observed. So here at the bottom, I'm showing an example, very high signal-to-noise, very large telescope spectrum of a quasar. This is flux as a function of observed wavelength. And so emission lines here are intrinsic to the quasar, but the many absorption lines that you see are due to this gas in between the quasar and the observer, right? And we see a lot of Lyman alpha absorption to the left of the Lyman alpha emission, but we also see a lot of metals, right? Now, quasar absorption spectroscopy is very powerful for 3 reasons. First of all, we do a direct accounting of the atoms, right? So we count the number of atoms along the line of sight in hydrogen, but also in metals, magnesium 2, carbon 4, iron 2, and therefore in different ionization states of a gas. Therefore, we can measure the temperature and the metallicity of that gas very accurately. The second reason why this technique is very powerful is that we can probe very low density gas that would not emit a lot of flux otherwise, right? So it's very powerful to probe this diffuse gas. And thirdly, the technique sensitivity is independent of redshift. As long as you have a bright background source, even at high redshift, you are as sensitive to this gas as you would be at lower redshift. Therefore, we have a technique that is very efficient in probing the gas over cosmic time. So here is a plot that made it to the figure 1 in a little review that Chris and I wrote a few years back that is kind of capturing what we've learned about H1 so far. Here in the middle, this is a foggy simulation of a galaxy at redshift 2 that is going to evolve into a Milky Way at redshift 0. And I have color-coded the map according to the column density. So the high column density gas is in green here, and slightly lower column density gas in purple, and then the more ionized gas in blue. So the top left panel shows the column density distribution of gas, both H1 and H2. So this is the number of objects of a given column density. There are many more smaller column density and fewer large column density. And at very large column density, H1 is taken over by H2. So we are seeing the formation of molecular hydrogen from atomic gas. Now this quantity is very well represented in cosmological simulation. Why is that? Because it's mostly driven by gravity, right? We are looking at the collapse of structure, and this is something that is well understood and well simulated today. The top right panel is showing the relation between the column density and the volumetric density. And so there is a direct link, right? The higher the column, the more density of the gas, the higher the density of the gas. The top the bottom right panel, is relating the neutral fraction with the log of a density, the volumetric density. So what's happening is some of this H1 gas is dominated by neutral atomic gas, but some of this H1 gas is mostly ionized, and we observed the neutral fraction of it, but can very accurately reconstruct the ionized fraction that is not observed directly. So this is also a well understood process. And finally, on the bottom left, you see a plot that indicates the relation between that gas and galaxies. So here, we're looking at the radial profile of H1 and H2 in typical galaxies in TNG. And so again, H2 dominates at very low, small r in the center of galaxy. H1, is much more extended at large radii. But I think this is key to try and understand and relate the gas and the galaxy properties. One point I would like to make is that we have now been able to observe some of that gas at high redshift in emission through Lyman alpha with very deep Muse field. This is work from the Muse GTO collaboration. This is work led by Lutz Wysotsky in Potsdam. And what they've done is they've done 100 hours exposure of one piece of the sky and look at all of the Lyman alpha at high redshift that they could probe. This is shown on the right here, in the blue area that you see are the Lyman alpha emission. What's interesting in this result is that if we compare, as shown here on the left, the incidence of those quasar observers given a column density cut, you see these green points as a function of redshift. So the large, the point at the top, the green points at the top are for Lyman limit system, column density greater than 10 to the 17. And as you go to higher column densities, there are fewer systems per unit redshift until you go to the large H1 observer, 20.3. But if you do similar surface brightness cuts in Lyman alpha, you can reproduce this absorption observation. So we now have a match between the gas that we observe through Lyman alpha absorption and the gas that we observe through the Lyman alpha emission, which I think is a very neat result. Now let me move on to the more global quantities. We've seen this, I think, yesterday or the day before already. We like to quantify the amount of gas in the universe in terms of omega matter. This is the mass density of a gas phase at a function of redshift. I'm showing omega H1 here. On the y-axis, you see it in units of 10 to the 8 solar masses per cubic megaparsec. And on the left y-axis, I have divided this by Rockrit at redshift 0, which means that it's now a unitless quantity, but also it means that if it's flat, it's not evolving with redshift, right? So the effect of the cosmologic evolution is taken into account. So again, the gray point here are measurements, observations at redshift less than 1. They are from 21 centimeter emission at radio wavelength. And all of the high redshift measurements are from these quasar absorbers that I've just described to you. I do think that we have now very accurate measurements of omega H1, and this plot is already, only 4 years old, but aged very rapidly. We've seen a lot of new excellent results on measurement of this quantity, so I think this is a booming field. I also think that it would be very important to have those two techniques overlap in redshift, right? I think the SK precursor and ultimately SK itself will make measurements at higher redshift where we have constraint from quasar absorption techniques, and it would be very important to then, secure, that those measurements are consistent with each other. The one point I want to make is I think we have an indication that actually the quantity of neutral gas, atomic gas in the universe is evolving very little over a very large look-back time. So one point I'd like to make is the absorption techniques I've just described to you is not going to work at high redshift because essentially beyond reionization, the quasar flux is totally absorbed, right? So one question we've been asking in the last few years is how are we going to measure the atomic gas above redshift 5? And to address this question, one of my students, Benedetta Casavecchia, has been working on this new set of simulations that we call ColdSim. They are fully time-dependent non-equilibrium chemistry, cosmological boxes that we evolve to fully process on the fly the H2 molecular gas. And then she goes on and computes the C+ emission from that output from the cosmological simulation. So what she's plotting here for two redshift panels, redshift 10 and redshift 6 on the right, is which of a gas fraction is most contributing to the luminosity of C+ that people observe through tools like ALMA. And you see here in green the ionized gas, in blue the molecular gas, and in yellow at the top the atomic gas. So what Benedetta finds is LC+, for C+ luminosity, is tracing atomic neutral gas. So this is an excellent tool to look at and look for H1 at very high redshift. I'm going to go back one slide, if I can, to also go back to this point of the little evolution of H1 with cosmic time. If you look at the inset now, this is the rate of change between the quantity of H1 gas in green and the mass in stars in pink, as starting from redshift 5. So what you see is that the quantity is shallower in H1 than it is in stars. So what this is saying is that the rate at which we are consuming H1 is not as fast as the rate as we are building stars. Why is that? I think the reason for this is because there is an intermediate phase, right, between H1 and star forming, and that phase, of course, is H2. So we have, many groups been looking at using ALMA and looking blindly for CO emitters that are a tracer of H2 and build the very same quantity for molecular gas. This is omega H2 now. So I'm showing this quantity, omega as a function of redshift. The boxes are a number of deep fields from various surveys led by great teams using the Aspects and Goldzy and other surveys. You see this is very difficult, challenging measurements to make. One reason is that we're using CO as a tracer for H2. Another reason is we have using deep fields that are prone to cosmic variance. But I think we are making great progress on this quantity. What I'm highlighting here in orange is work from another PhD student, Victoria Boyo, who's been using ALMA-CAL, which is this survey that essentially makes use of the ALMA calibration fields for amplitude and phase calibration, on which ALMA is spending a lot of time, actually. And what we've done is we've gathered all of this data. This is over 2,500 hours of ALMA time. We've moved the calibrator, and then we use those deep, sometimes very deep fields to look for CO emitters. Now, what's powerful about ALMA-CAL is shown here on the right is that the sight lines are all over the southern hemisphere sky. Therefore, we are very little prone to cosmic variance in this survey. And here results that are very early on now are shown here in orange. This is an ever-growing survey, of course. So as we speak, more data are being taken, and ARMACAL is growing. So it's a matter of catching up with this amount of data. But I think it's very powerful, complementary to the deep field results that we've been seeing in the last few years. Of course, simulating omega H2 is very challenging. Again, for reasons I've given earlier, we need, big box to have a cosmological context, but we need to resolve small-scale physics that is not very well understood, but also very computing demanding to have a full H2 on-the-fly production. This is an effort that we've been doing, indicating in red the result from turning on this non-equilibrium chemistry, which I think is done a slightly better job at reproducing omega H2, and I'm very much looking forward to upcoming simulations that will be able to do this even at lower redshift. Now, this plot, I think, is maybe one of the main messages I'd like to convey. This is putting everything together now. So this is again omega, this is again the mass density, but here on top, the blue is the total amount of baryons. This is very well known from 3 different measurements done at different redshift. One is the cosmic microwave background anisotropy from Planck. The other one is Big Bang nucleosynthesis, a measurement of deuterium. And the last recent one is measurement of dispersion measures along fast radio bursts. All of these measurements convey toward the same amount of omega of baryons in the universe, these omega baryon values. This is well understood. Now, most of the baryons, if we cut them down into phases, which is the goal of this exercise I'm showing here, is ionized. Most of the baryons are ionized. And I'm not showing this here because I'm concentrating on the phase of baryons that are closer to the building of the stars. So again, what I'm showing here in green is the atomic gas. In gray is these early measurements of a molecular gas, and in pink are the stars. So one point here is that the shape of a molecular gas is very much like the star formation rate history. So there is a growth, going from high redshift with a peak around redshift 2 to 3, and then a dramatic drop, which is counterintuitive, right? You would expect that we keep forming stars, and yes, both the H2 reservoir and the star formation rate are decreasing at low redshift. And I think the two are linked, right? Some of the star formation rate drop at low redshift may well be due to this lack of direct reservoir to make the stars. The second point to take away from this plot, which I think is the most important point, is at any redshift in the universe, omega H1 is above omega H2. There is more atomic gas in the universe than molecular gas at any redshift, right? Now, you're going to tell me, where is this H1 gas? Maybe it's not in galaxies, right? But I think it is. And the reason why I think it is the following. This is work from Saloni Deepak and other students in the US. She's plotted here the contribution of quasar absorber of a different colon density to the total amount of omega H1, right? And she's done this for 2 redshifts. In blue is redshift 0, in red is redshift 3. And so what we see here is that most of the mass of H1 in the universe is coming from very high colon density system, peaking at 10 to the 21. 10 to the 21 is not CGM gas. This is ISM gas. These colon density are inside galaxy. They may be small dwarf satellites of a central, but they are still galaxies, right? So most of the gas in galaxy is neutral atomic. So essentially what I'm saying is that when we are saying, take a redshift 2 to 3 galaxy for which we have very accurate H2 measurement, and we argue that we are studying the gas in that galaxy, I wonder if we are not concentrating on some phase of a gas that may well be for some objects the dominant one, but overall, there may be a large reservoir of H1 gas in those galaxies as well. So I think this is something to keep in mind. Now, of course, this picture is not static, right? Those phases of gas are cycling. What do I mean by cycling? I mean, they're moving in and out of galaxy, but they're also changing phases, right? And so we can capture those movements through the phase gases, through this quantity that we call the gas depletion timescale. This is essentially, as shown on the equation on the top, the amount of gas divided by the rate at which we transform that gas into stars. Now, most often, people have done this for one object. We measure the gas mass of that object, we measure its star formation rate, and we can deduce the time it takes. And an example of this is this dashed black line here, which is a result from Tacconi et al. With very accurate measurement of time depletion scales in massive galaxies. What we've done in this work together with Chris is to look at this quantity globally, right? So we know the amount of gas, we know the amount of stars being formed in the universe. What is the global depletion timescale? So in green, I'm showing the cold gas depletion timescale, that's H1 plus H2. And in gray at the bottom, you see the molecular depletion timescale. And what we find is that if we concentrate on the last phase of a gas before it forms stars, that quantity is very flat over a very large look-back time. So essentially, there is something universal in the way we convert the gas into stars. And this is very consistent with measurements in individual galaxies at low redshift. We can go one step further and now ask the following question. I have observed how much gas there is, how much stars there are. How much more gas do I need to put into the system to explain the extra mass in star I observe, right? This is what I call the net accretion rate, and it's shown here in purple as a function of redshift. This is actually agnostic about whether this is gas moving from the galaxy or whether this is gas going from ionized to neutral, right? So I cannot tell the difference. This is just how much gas I need to explain the star we observed. What I think is interesting is if we look at the dark halo accretion rate shown in black here and scale it to the efficiency of only 4%, then we get the dashed line at the bottom. So essentially, we are saying there is, again, I think it's been said before, the baryons are very, very inefficient in turning into baryons. This kind of results, I think, are very much in line with what people have been arguing, the so-called bath-tube regulator model, where there is an equilibrium between the intake of gas into the system and the star formation rate that is consuming that gas. Now, I'd like to, in a few minutes I've left, move from the global scales to the more galactic scales, right? And I'm going to show you that the galaxies, are fed in gas through these gas accretion processes, through cosmic web filaments, and in turn, this gas is, cooling down and then driving star formation that will itself drive supernova feedback and AGN feedback that will pollute the surrounding medium with metals and different phases of a gas. And this is what we call the circumgalactic medium, this region of a gas around galaxy where this phenomenon takes place. The question, obviously, is how do we relate what we learn from the absorption with what the galaxy look like? And so one great progress that came up in the last decade, I would argue, is the use of integral field spectroscopy, which is an image where every pixel is also a spectrum. And I think one of the true game changers in the field has been the MUSE instrument and the very large telescopes, which is this very large optical IFU. And other groups and our group have been using MUSE and in combination with other facilities such as HST and ALMA to probe the multi-phase gas around galaxies. So we have in particular been interested in selected on strong neutral gas absorbers and observing the galaxy associated with this gas, with MUSE at ionized, in the ionized phase of a gas, but also using ALMA to get the molecular gas. And we've been allocated a large program to do this recently. So what are we finding? This is work from Simon Wang, another PhD student of mine, who's plotting here the number of absorbers that have, as a function of the number of galaxies associated with this H1 gas on the x-axis. So what we find, much to my surprise, is that more often than not, we don't find one galaxy associated with the quasar observer, but multiple galaxies, right? Because again, the IFU is very powerful in identifying and measuring the redshift of this object very quickly. Ramona Augustin, who used to be a PhD and a postdoc in Potsdam, is been measuring using this HST broadband imaging to measure the stellar mass of these objects. So I'm showing here the stellar mass of a sample as a function of H1 colon density. Those are pretty standard objects, but they have a large range of stellar mass, going from 10 to the 8 to 10 to the 12. And the 10 to the 8 in limit is probably an observable limit in our HST data. So we are probing also very small objects. Now, what I think I would like to highlight in particular is the IFU again provides kinematic information of this gas. So I'm showing here one object for which on the top left we see the continuum from HST, the middle top we see the H alpha emission from MUSE, which I've been forward modeling to get the velocity map shown on the top right. So this is using MCMC tool in 3D space that is looking for optimizing and forward modeling a disk, rotating disk in this object. And of course, this work that we've done in H-alpha, we can do with CO as well, and that's shown on the bottom. This is the CO1 to 0 detection from the spectrum. This is the image in the middle and the rotation field on the right. So what we see is the molecular gas is much more restricted to the center of the galaxy as expected. The rotation axis and directions are very similar in the two phases of the gas. But if you pay attention to the color axis here, the velocity max is doubled in H-alpha than it is in CO, right? Very interestingly is this work, for example, which is looking at another object where, again, I'm showing the velocity map. And here in black is the position of a background quasar. What I'm showing here at the bottom is a normalized spectrum of a background quasar with a velocity scale such that at 0 is the systemic redshift of a galaxy, right? And we see two components in this absorption profile. This is magnesium-2 absorption. This is 10 to the 4 Kelvin gas again. The stronger component happened to be at a velocity of 100 kilometers per second, which very nicely match the disk rotation, right? So in absorption here, we are just looking at gas rotating with that disk. But there is another component which has smaller velocity, less metals, and a higher angular momentum. So we think this is the kind of signature of gas accretion on top of a rotation that is probed. So what is my mental picture of this? I think it's very much alike what we've been hearing in the last 2 days. If we just focus on optical wavelength, we see a bunch of galaxies that appear to be connected. But if you look at radio, then of course there's a lot of H1 gas. Some of it is very diffuse, difficult to observe in emission at high redshift, but possible to observe in absorption. And if we zoom in on galaxy, we also have, school case example of galactic winds, which are processes we are very much interested in probing to understand this baryon cycle. So in the interest of time, I want to just show that last plot that is showing how we can map the H1 around galaxy by using the power of statistic. So this is now a plot where at the 0, 0 left axis, you have a position of a galaxy. And then we're measuring how much H1 there is as a function of impact parameters, so the distance between the quasar sightline and the galaxy, and delta V, which is just the velocity along the line of sight. And we can now map, this is the color axis, the strength of these H1 absorbers. So I think the one pencil beam technique can be beaten up by having a very large number of systems, and foremost in particular is going to help us acquire 1 million quasar spectra to do this kind of science. So I won't take more of your time, but I would like just to put up the conclusion that please remember H1 dominates H2 content of the universe at any redshift. Baryons are not static, they're cycling through different phases. And of course, we have now the mean to map the H1 gas around galaxy at high redshift. Thank you very much.
Thank you very much, Celine. I think we need an hour to listen to you to understand fully what's going on. And I'm pretty sure we have a lot of questions, but not that much time. So please raise your hand, say your name, and ask your question. Enrico, I'm coming to you.
Hi, Celine. Thank you very much for the very nice talk. So I was wondering, in the case, in the galaxy that you show where you have the rotation curve and then you have 2 absorption along the line, one particular line of sight. So is there any particular reason why you think that the lower velocity absorption is something that is accretion and not something else like extraplanar gas or outflow? Why not? I mean, could be anything.
Very
right?
good point. So there are three reasons why we think it's accreting gas. The first reason, so it's different velocity than I would expect from the disk rotation. So it's not disk rotation. That's one first point. But the other point is that component is metal poor. So what we've seen in TNG and Eagle is if we look at how much, what's the metallicity of the gas falling into galaxy and what's the metallicity of the gas outflowing from galaxy, there's a strong metallicity bias. Obviously, the gas get enriched with metals as, within galaxy where star forms. And therefore, the fact that this component is much more metal poor than the other one is, I think, indicating towards accretion rather than outflows. And the third point is that we've been able to measure the angular momentum, which is 2 to 3 times larger than the other component. So I think this is another reason why we think this is gas accretion, indeed.
It's Andrew Baker, Rutgers University. I was really interested in your demonstration that there are multiple absorbers, multiple galaxies associated with individual absorption line systems. Are there things that we thought we knew about absorbers, like, for example, enrichment histories that are now thrown into doubt by the fact that there are multiple galaxies contributing to those single absorption line systems?
Yeah, thank you, Andrew. I think that this is a good point. I do think that the picture globally complexified, right? And that's what I try to show with this mental picture. I think, some of these gas, has to be related with the CGM of a specific object. And maybe we are probing rotation, gas that is rotating, maybe we are probing inflow, outflow. But because of some of the impact parameters we measure, despite being very deep in finding, low mass object, some of these gas may also be the diffuse gas that is seen, with these beautiful meerkat maps at, in between galaxies, that is the remnant of, some interaction between those galaxies in the past and so forth. And so the question is how to disintegrate these different things. We've been working on, simulation to try and help us get information based again on metallicity and velocity differences to identify this gas case by case. And I think this is very much work in progress.
Unfortunately, we're out of time. Please come and talk to Celine about all the questions or all the answers maybe you have for her. And let's thank her again for this wonderful talk.
Thank you.
Our next speaker is Dan Fisher, who will tell us about the cold gas outflows in the galactic disks.
All right. I should start by saying that pretty much all of this work is from my postdoc, Barbara Mazzilli-Corallo. So there is basically a consensus that you can't make a galaxy without feedback in galactic winds. This is a plot of the star formation rate density versus redshift. The points are data. And the lines are a very clever thing that was done by the TNG group, where they went in and turned on and off the different sort of forms of feedback, similar to what Ramil showed. And the orange line is what happens when you turn off the galactic winds. You get star formation rates that are literally off the charts. And that means you get outrageously high masses. We also know the sizes, the morphologies are all wrong if you don't include galactic winds. So they're incredibly important, but the problem now happens that we don't really know the details of how they work. When we look at the nearest galaxies in the universe, here's this great picture of M82. The red is cold phase gas, it's dust from Spitzer, and the blue is X-ray gas. We know that observations of H1 and CO tell us that most of the gas that is leaving the plane of the disk is in that cold or neutral phase that's coming out, especially in the H1. And once that gas is out of the disk, it's no longer available to form stars. So this is doing the heavy lifting of regulating the star formation. This creates a problem or a feature of studying outflows. And it's that the colder gas is not moving at super high velocity. It's moving at a few hundred kilometers per second, which is not enough to escape the halo. And so it's not going to just simply shoot out of the entire halo and quench a galaxy. What it's going to do is move up into the CGM, do some stuff there, cool, and come back down. And so that means it's no longer enough just to measure mass loading factors of galaxies. We have to understand how the outflows work, and we have to have a kinematic model for the winds because we need to give simulators and theorists that time something that they can get that time scale for how long it comes back down. And there's a growing idea that the interaction between that hot gas and the cold gas and the interaction across the phases is critical for setting the kinematics of the wind. And so we need to study that. M82 is great. It's the best galaxy. That's why you see it all the time. But we need to look at more galaxies. This is one more. We will eventually get to the concept of studying many. This is NGC 4666. That's an H-alpha narrowband map, courtesy of Eric Pang and Zheng Wang. And you can see that X shape coming off the galaxy that we believe are the limbs of this bicone. So you have a hot X-ray wind with a H-alpha bicone going around it. So this is what winds look like. And just the plot over here on the right is just to orient you to the kind of environments that we're talking about. So it's star formation rate, surface density versus molecular gas surface density. The gray points are Fangs galaxies. So this is what a typical spiral is, and the blue is this galaxy. The filled blue is the region underneath the outflow. So we're talking about star formation rates that are orders of magnitude higher than typically is what in a spiral, and that's where you need the outflow to do the regulating of the wind. We're going to study it with GECKO's data. Celine just gave an excellent introduction to MUSE. GECKO's is a MUSE large program studying edge-on galaxies, and a key feature of it is its very deep exposures, many, many OBs per galaxy. Moment zero map of Wallaby from Lee et al. This is again courtesy of Zheng Wang. And just to sort of orient you to the kind of things we're looking at, this is about the best you can do on H1. On an outflow right now, this is M82 from Martini et al. What we see, these kind of, they're marginally resolved, they're fuzzy little features, but they exactly overlap with where those H-alpha limbs are. Also, we can look at the kinematics of the H-alpha and the H1, and there's about a factor of 2 offset that the H1 is moving slower. That's what you expect. That's similar to M82, but what I think is nice and interesting is the wiggles in the profile, the substructure in the H1 velocity is also seen in the H-alpha. There's no reason from the observations that that should be there. And so that's really nice, and it makes me confident that the H1 I'm seeing in that fuzzy moment zero map is actually gas, that it's experiencing a similar kinematic structure as the ionized gas. And so I feel confident that we're actually measuring the outflow with the Wallaby data. So now we can get at the questions that we want to answer with the data. And the first is on the left. What I'm showing you is the mass outflow rate of the outflow against the distance from the midplane. And there's many things to pull out of this that tell us a little bit about how the outflow works. The blue line is the H1, And the magenta region is the ions. There's a lot of systematic uncertainties in estimating the mass from ions, and so you have a region there. And one thing to see, obviously, H1 is dominating the mass loading of the outflow by a lot, by an order of magnitude. That's actually a lot more than M82. M82 they're kind of closer together. The other thing is the H1, and they're kind of a constant offset. Okay, there's a wiggle in the H1, but given the systematics in the ions, that means the mass loading is sort of consistent. There doesn't seem to be this outrageous amount of heating that's happening in this outflow as you get further from the disk. The other thing that's, of course, very important is that dashed line going across the top of the plot is the star formation rate underneath the outflow. And so what you can see is in this galaxy, in that really high star formation rate region, the mass that's leaving the galaxy in the H1 is doing the dominant form of regulating the star formation. So this is telling us that H1 is super important for understanding the galaxy evolution of these systems. If you remember anything about this plot, it should not be that wallaby-gecko hybrid. It should be that idea that H1 is the dominant, is doing the heavy lifting on galaxy regulation in winds. We look at the right, we convert to global mass loading factor, so that's the plot on the left divided by star formation rate, and then you kind of measure it a little different. But it's just to compare to unresolved measurements to make sure what we're seeing is somewhat normal. The unresolved measurements, all the other points on this plot, are mainly ionized gas, so you should look at the magenta points, and they're pretty much consistent with the kind of mass loading that you expect for this galaxy's mass. The two dashed lines are results from the fire simulation, so the one on the bottom is for ionized gas-ish, and it's consistent. But when we look at the H1 mass loading, it's a bit more than what's in the fire simulation. So in simulations, they generally find very fast, high energy mass loading that takes the gas pretty far out in the galaxy. What we find is very high mass loading in the H1, but moving at lower velocity. So it's not going further out. So there is really a mismatch between what the big box simulations are doing and the results we're seeing in the mass loading, and that is most revealed by the H1. Now we can look at energy loading. And so here, this is informative. You have an energy from your star formation rate. You have your, a number of supernovae exploding in your galaxy. And then that injects energy into the ISM, and you can estimate how much that is based on some assumptions and knowing the star formation rate. And then that energy should be larger than the energy you measure, the kinetic energy you measure in the wind, larger by a fair bit because it won't be 100% coupling. If it's not, then you have a problem, or maybe there's an AGN that you're missing or something like that. And so over here, we do the energy loading, so E dot out versus distance from the midplane. When you add together the ions in the H1, you get about 20-25% of the energy from the star formation. That's a good number. That's consistent with what other people find. But again, another difference between M82 and this galaxy is that there's a lot more energy in the cold phase gas. In M82, the energy loading is about an order of magnitude higher in the ions than it is in the H1. And that's very different than this galaxy, where they're about equal. I don't know why that is. It's one galaxy. I don't know if that's important, but again, sort of bringing us back to this idea of what we're learning here. We have this result with the electron density profile that is crazy different than what is expected in theory. And then whatever we do, we are working with theorists, we're working with Drummond Fielding to try to figure this out. Whatever we do to try to solve this will probably impact the balance of the phases and the cooling of the gas. So we need to understand, is this normal? Is this a thing we see in other galaxies? This galaxy has higher mass than other galaxies with outflows that are resolved. Maybe that's important. But the future is really bright for this subject, obviously. So SKA will give us better resolution, better sensitivity. And so when we go back to galaxies like this one, we'll be able to get highly resolved observations of the H1 across the filament, and we'll understand how the heating is different in the inner part of the outflow and the outer part. That'll be super important. But another thing that's very important is studying samples. For me, one of the things that makes outflows so hard to study is not just that they're faint, is that they're so rare. And so in order to build up samples to understand how these things vary with different properties of the galaxy, we need to go to further away. And I chose Wallaby data for this demonstration on purpose. It is an all-sky survey. It is shallower than targeted observations. It is not the highest resolution data. But I wanted to show that we can still derive physically intuitive things and important things from this, so that because we are already building these samples of ionized gas outflows across many galaxies. And when we want to follow this up at lower spatial resolution with SKA, we will be able to do that in the future. So I think I'm out of time, so I'll just stop there.
Thank you very much, Dan, for such an exciting talk. Do we have questions in the audience? Yes, you? Okay, thank you.
Hello, I'm Jake Bennett from the CFA. Very interesting talk. I guess you sort of alluded to this towards the end, and you might not have an answer yet because of samples, etc. But how representative are M82 and the other galaxy, the NGC galaxy that you've shown, of the wider galaxy population at low redshift? Or are they particularly high star formation rates, or, for example?
This is my point. Yeah, we don't know. We need samples. So they're starburst galaxies, right? So in the local universe, if you want to study a biconical outflow, you have to look at starburst galaxies, things that are rare. But it's important to realize what's rare in terms of starburst locally, in Celine's talk, becomes the normal galaxy at redshift 1 and 2, where most of the stars are forming. So rare is a very relative term to what you're studying.
We have a question on the back, the last question, unfortunately.
Very nice talk. Regarding the H1 mass loading factor, you showed that the mass outflow rate of the mass loading factor are going down a certain KPC. So in cosmological simulations, I think that we expect those values to be really high, like mass loading factor of the order of 10, right, at 10 KPC. What do you think is the connection between the observations of starburst and the cosmological simulation? So just to conclude, to summarize, do you think that we are able to reproduce the galaxy stellar mass function with those mass loading factors?
So there's multiple things in your question. The first is simulations do reproduce the stellar mass function with what they have. But this difference between simulations and observations is known. There's a difference between the cosmological simulations and the high resolution simulations in terms of the outflows they put out. And there are differences. Our cold outflows move slower than what's in the simulations. The simulations also the big simulations don't resolve the cold phase necessarily, so you become very susceptible to whatever prescriptions they're using. And so exactly what the reason for that difference is, I don't know, but it is different.
Thank you very much. Let's thank Dan again. And from disk outflows to radial flows within the galactic disk, we have Enrico Di Teodoro.
Okay, can you hear me, guys? Yes. Okay, so thank you, Anastasia, and good morning, everybody. So today I would like to present this work that I published just a couple of years ago in collaboration with Josh Pick about radial accretion in star-forming galaxies in the local universe. And also because I think this is a classic and pretty neat science case that it will be possible to investigate in much more detail and in a much more accurate way in the near future, thanks to the next generation of H1 surveys like Mongoose, but ultimately with the SKA as well. Okay, so Diane just showed us that there are beautiful outflows in galaxies, but another very important step in the so-called gas cycle is gas accretion. And why do we need gas accretion? Well, we know that star-forming galaxies, they need to accrete gas from the surrounding environment to sustain their star formation in the main disk. And this is just because, at least in the less in the last few giga-years, there is just not enough cold gas locked in galaxies to sustain star formation for very long. For example, in the Milky Way, we have something like a gas reservoir in cold gas of 6, 10 to the 9, and with a star formation rate of 2, 3 solar masses per year, that would last just a couple of giga-years. So we need gas accretion. The first possible channel for this is mergers, of course, and in particular minor mergers, because you don't want to destroy, and to change the morphology of the galaxy. But so we know that spirals have many companions. They are dwarf-rich, as the H1 tells us. But unfortunately, if you try to count how many dwarf galaxies there are and what kind of masses they have, you will see that actually they could not bring too much gas into the main galaxy. So they can contribute up to about 10% in the very optimistic case. So this is not enough. So the second possibility is actually direct accretion from the intergalactic medium. In fact, the theory and the cosmological simulation in particular show us that there could be cold filaments that penetrate the halo. And while they do that, they are subject to the torques of the rotating halo, and they can settle in a rotating disk at very large radii from the star-forming disk. Of course, what you need to do next to form stars is just to bring this gas to the star-forming part of the disk, so to the inner regions, right? So you expect some amount of inward radial gas flows in star-forming galaxies. And if you want to do, for example, 50 kpc, and you do it in a very slow way, so let's say 5 giga-years, that would imply an average radial flow of 10 kilometers per second, which should be measurable with current observations, right? Unfortunately, this exercise is not easy to do, so because you need to measure a quantity that is an order of magnitude or more or less than the general rotation of a galaxy. So there have been a few studies trying to do that on small sample of galaxies, and unfortunately they did not reach a conclusive evidence for gas accretion. So we try to tackle this problem with a bigger sample of galaxies. So here is the recipe to measure radial motions. You need, first of all, a gas tracer that goes very far away from the galaxy center. And of course, H1 is the best tracer because H1 disks are much more extended than optical disks. So you need H1. You need very high quality data. Okay, so first of all, you need high sensitivity. You want to probe the very low column density gas in the outskirts, so deep observations. And you also want high resolution, both spatial and spectral resolution, because you want to be able to do a very accurate model and to measure very small radial motions in these systems. Together with the H1, you also may need some optical data, because optical data can tell us which direction the galaxy is rotating. Emission line alone don't tell you usually if the galaxy is counter-rotating, it's rotating or anti-clockwise rotating, and this is an information that you need if you want to understand if the radial motions are inwards or outwards. Okay, so we collected basically a bunch of galaxies from the literature. So these are all archival data that have good enough data for this kind of study. It's 54 galaxies, star-forming galaxies with a range of stellar masses from 10 to the 9 to 10 to the 11, and they also live in different environments. We have the data. Now what we need, of course, is a kinematical model. And I guess many in the audience can probably guess which kind of kinematical model I'm going to use. So no surprise, I'm going to use 3D Barolo. And of course, it's not the only code that does that. What you need is a 3D fitting code. There are many. And what you want in particular is a software that can do both rotation and non-circular motion at the same time. Okay, just for those of you who are not really familiar with galaxy kinematics, I want to show you what kind of feature we are looking for. So in general, you have a stellar, like a disk, okay? It's rotating with a regular rotation, let's say a flat rotation curve. You have your emission line observation, you derive the velocity field, and it shows this very beautiful and well-known spider diagram, okay? So with the isocontour lines like this. Then you extract the PV along the major axis, and you see the beautiful flat rotation curve. And you do the same along the minor axis. You see basically just the velocity dispersion of the gas, which is increasing in the center because of the beam smearing. Okay, now we add some degree of radial motion to this perfectly rotating disk. So let's say that at some radius we start and we increase the radial velocity of the gas, because this is what basically the simulation predicts. And what's the effect of this? It's just this very small deviation on the minor axis of the systemic velocity with respect to the geometrical minor axis. Okay, so this is the signature that gives you evidence for radial motions. You don't see much on the major axis. You see the same kind of deviation in the isocontours in the minor axis. Unfortunately, galaxies are not perfect disks like these ones. So most of H1 disks have very huge warps that cause a very similar deviation of the minor axis. So if you have, for example, a warp in PA in the position angle of your galaxy, you see the warp mainly on the major axis, but also on the minor axis. And this is pretty similar to what you see here. And so in the natural situation, what we will have to deal with is both a warp and radial motion. So again, you have the deviation from the on the major and minor axis, and then on the minor axis, you are going to see a further deviation due to the radial motion. This is the kind of feature that we need to find. Okay, so first of all, we need to model the warp, find the best model possible for the geometry of the galaxies, and after we have done that, we can try to look for this kind of feature. And it can be even more complicated if you have an inclination warp. Okay, so just to tell you very small details on technical side, so we used at the end of the day a three-step approach. So we first fit the geometry of the galaxy, so the inclination and position angle of the warp. We fit then the rotation curve, giving more emphasis on the major axis, which is where the information on the rotation lies. And finally, we just fit for radial motion on the minor axis. Once we have the model, we can put it together with the H1 surface density profile that you extract from the geometry that you derived. You put everything together, and you can calculate a mass flow rate in that galaxy, a radial mass flow rate, which is basically you have how much mass in a given radius is flowing inwards or outwards. Very simple. I'm going to skip this. Okay, so just an example in one very well-known galaxy. This is NGC 5055. Everybody knows it, probably in the H1 community, because it has one of the most extreme warps in the local universe. So this is the optical image, which tells us that the galaxy is rotating clockwise, and this is the velocity field with a big warp. So you do your model. First step, you get the position angle and inclination right for the warp. Then you fit rotation. You derive the surface density profile, and finally you just focus on the radial stuff, derive the radial velocities, and put it together to get the mass flow. And at the end, you have a very nice model that reproduces your three-dimensional data cube. This is all done in the 3D space. Okay, so let's go to the results. So we did this kind of exercise for our sample of 54 galaxies. And what we found is this one. Okay, so in this plot, upper panel is the radial velocity that we measure as a function of radius, and the mass flow rate as a function of radius for the entire sample of the 54 galaxies. So each black line is one galaxy. And positive values means outflows, actually radial outflow, so stuff that it's moving outwards, and negative stuff means inwards radial motion. And as you can see, of course, there is some degree of radial motion. I mean, H1 disks are messy, but I mean, there is clearly no widespread inflow signature. Okay, if there was like, so if all galaxies were having inflow accretion, you would see a lot of stuff in the negative part of these plots. And this is also evident from the red line, which is just the average overall the galaxy. It's very much consistent with being 0 in both the mass flow rate and the radial velocity. And you can see that also in these histograms, which are just average over the population taking a different radii, so increasing radii. In particular, the most external radius is this yellowish thing, which is just the radius where the H1 columns drops below 1 solar mass per parsec square. And as you can see, these distribution agains are close to 0. Okay, so there is really no signature of a common inflow in all these galaxies. And finally, what we can do is just to compare these mass flow rates that we measure with their star formation rates. So in this plot here, we put the mass flow rate in this y-axis, while on the x you have the star formation rate. And in the blue region here, this is where you have actually outwards radial motions. In red, you have some inflow, but the inflow is not enough to sustain the current star formation rate. And the only region where you can actually accrete enough gas radially is the region in yellow here. So there are just 3 galaxies that have enough radial accretion to sustain the star formation rate. While most of them is like maybe they have some, but it's close to 0, and others they actually have average outflows. Okay, so yeah, okay. If you do the entire average, you are going to get a radial accretion of 0.1 solar masses per year, which is an order of magnitude again less than the average star formation rate of the sample. So coming to my conclusion, I just have one take-home message, which is Houston, we may have a problem here. Okay, so we cannot accrete gas from mergers; they are not enough. We do not accrete gas radially, as the theory predicts. What's happening here? How do we sustain the star formation? So I'm just, speculating 3 possible solutions here for why we don't see radial accretion. Maybe gas accretion is not radial after all. Okay, maybe it's vertical. This could happen, for example, if you are able to cool down the corona or the circumgalactic medium. Maybe you are just accreting vertically, and this kind of accretion is very, very difficult to detect from a kinematical point of view. So maybe that's a possibility. Second possibility is that, okay, maybe gas accretion happens, but it's not a secular process. It's not like you always have gas flowing into the halo. Maybe this happens once in a while and on very short time scales. In this case, we will not be able to see it in a statistical way like we are trying to do. Finally, last possibility is that gas accretion is actually fading down. Okay, so maybe galaxies today, they are not accreting gas from the intergalactic medium anymore like they used to do, which also would imply that star formation in general would be declining, and at the end of the day would be fading completely from star-forming galaxies. I think that's all I have. Hopefully, SKA will help us with these different scenarios, and we'll be able to, at the end of the day, to understand gas accretion in a proper way. Thank you very much.
Thank you very much, Enrico, for this fantastic talk.
Yeah, thank you. Very interesting. You modeled the disk as a simple single disk, but many spirals have a thin H1 disk and a thicker H1 disk, the extraplanar gas.
Yeah.
And in some galaxies, we found that indeed in the thin disk there are no radial motions, but in the thick disk there are. Could you extend your model to look at this?
So, okay, as we know, that studying the extraplanar gas, you better have edge-on disks. Okay, it's easier. And edge-on disk, I think it's more difficult to find the signature of radial accretion. So maybe it is possible. It's even more uncertain than the one that we have now, I think. This is already very uncertain, I should say. So I'm afraid that if you add a further level of complexity, it would be even more complicated. But yes, it is something you could try. We could try, actually.
Very nice talk. This is Jingwan from KI in Beijing. I'm wondering, when you see the radial motion changing sign, do you see a piling up or emptying of gas at that radius?
So can you repeat, sorry?
For example, when the gas inflow and outflow to the same radius, do you see piling up of gas at that radius and vice versa?
This is just gas that is flowing in and flowing out at different radius. You just calculate the mass in a ring, you have the radial velocity in the same ring. It's an average, of course, it's not like local stuff, but yeah, and that's what is flowing in that particular radius. I'm not sure if I answered your question, but.
Okay.
Thank you. I'm Shishan Lin from Peking University, and I'm asking for your vertical accretion scenario. You mean most of them directly falling into the star-forming disk, or they falling onto the general larger H1 disk? Because in that case, they still need to radially flow into the center to sustain the star formation, right?
Yes. You mean the scenario, which one? The gas accretion at vertical? The first one, yeah. So if it's vertical, you can accrete basically already on the star-forming disk. Okay, so you don't have to really do a lot of radial motions to make it available for star formation. So that's why it could be a possible main channel of accretion.
We have the last question, and we are so happy that early career researchers are starting to engage. Enrico, you're the least scary speaker, it seems. So please keep going. You see, it's not very scary to ask questions.
Hi, Mikhail de Valles, UCT. I wanted to ask, is your study just confined to intermediately inclined galaxies? And do you, what's the validity in applying this to the extreme cases of the most face-on as well as the most edge-on galaxies?
Yeah, no, this is correct. This is limited to galaxies with inclination, I think, between 40 and 70-ish degrees, because, okay, you don't want to have face-on system because then you have very uncertain rotation velocity because the correction for inclination messes up the rotation curve, while you don't want to have too much edge-on galaxies because, of course, you're not going to see the minor axis well anymore. And the information there is on the minor axis. So yes, it's limited, and it's more difficult to do it at low inclination and high inclination. Yeah.
There is a lot of interest, so please come and talk to Enrico. As you see, he's not very scary. I've heard he knows a little bit about Barolo, so also students who are using it, please come and ask him questions, and let's thank him again.
Thank you.
Our next speaker is Julia Bluebird, who will tell us about H1 and H2 at higher redshift using Chile's survey.
Good morning. The use of high redshift is subjective. It depends on what you're studying. So if I say higher redshift, I'm referring to H1 higher redshift. So 20, it shows the cosmic densities for stellar and gas components as a function of redshift. And we know that the cosmic star formation rate peaks at a redshift of 2 and sharply decreases to the present day. But we don't know as much about the gas in these intermediate redshifts. And so the H1 gas density decreases by 2, the H2 decreases by 6. The area highlighted in this plot is the redshift that Chiles covers. And so if you look at the error bars, the stellar component is well determined. And we have few detections of H1 and H2 gas in these redshift ranges. So that's what we're trying to fill in with our survey. And so the samples that I show in this talk are are samples that have both H1 and H2 measurements. And so we'll be presenting for high redshift detections that we have. And we detect 4 gas-rich galaxies over the redshift range of 0.2 to 0.5. And these are 4 galaxies that we also have H2 measurements for. We study the morphology and kinematics using these resolved images in H1. We also did follow-up observations with CO. For these 4 galaxies with a LMT single dish, and this provides a tracer for the H2 gas. And we combined the sample with previous Chiles detections. And so we are adding 19 measurements of both H1 and H2 past the local universe. And so for the first time, we have a continuous look of the cold gas fraction out to a redshift of 0.5. And so Chiles is the Cosmos H1 Large Extragalactic Survey. It's a blind survey using the VLA and B configuration. It's a single pointing in the cosmos field, and it's of a redshift range of 0 to 0.5. Even at our highest redshift, the entire field of view is about 17 megaparsec across, and we have a linear resolution of over 40 kiloparsecs per second. I also want to highlight 2 studies that have been done around a redshift of 0.2, Buddies and High Z, and I will be referring to these points in our plots later on. So Chiles image is neutral hydrogen gas. In galaxies 5 billion years back in time, this is a galaxy that we have at z equals 0.47. You can see on the left, we have kind of a zoomed out image from JWST. We have the total gas contours here. And we are also able to get velocity information with the velocity and also the position velocity diagram here. These are very low signal to noise detections, and so I included the channel maps here. I don't know if this is showing up very well, but we do look for coherent contours in multiple channels, and so you can see these contours are moving along the major axis of the galaxy. And so this is amazing that we can make images of this and we can distinguish the different peaks in the H1 content and also have some velocity information as well. So this is a JWST image of this galaxy that I just showed you. It's zoomed in. This is with the 4 filters from NIRCam, and they're combined in this image. And the detail from this is incredible, but we can see more details that we can with the HST images that we've been working with. But you can see the spiral arm here, and you can see this galaxy is asymmetric. And what we see in our JWST images are these knots that appear, and these don't show up in the HST images. So this is really interesting to see in our JWST images, and it looks like this galaxy may be interacting, and the 4 galaxies in our sample have high star formation rate, so this might be a reason why we see that. These are other JWST images from the sample, and this galaxy here is a dwarf galaxy. It's at a redshift of about 0.3, and this has an H1 envelope that's 10 times the stellar mass. This is the image that I showed you before. This is just one filter from NIRCam, and you can see these little knots. This is another galaxy that we have at redshift of 0.25, and you can see these little knots show up in these images as well. So as I mentioned before, we did follow-up observations with the LMT. And so in addition to having the morphology and kinematics of these galaxies, we also now have the stellar mass, the H1 mass, and the H2 mass. So we're starting to get a lot of information about the story of these galaxies. So as I mentioned before, all of these samples have both H1 and H2 measurements. And so before Chiles, there's only 9 galaxies past the local universe that have H1 and H2 measurements and 6 upper limits. And that's these galaxies here. These local universe galaxies are from the Cold Gas Survey. And I have them, I only chose blue galaxies using an NUV minus R cut. So I'm trying to compare apples to apples and have the galaxies be as similar as possible in this comparison. And so we make a cut with the blue, and I divided them into low mass, low stellar mass, and high stellar mass. And so that's these galaxies here. And these are the Buddies galaxies. These are measurements taken from 2 clusters. And this is the High Z survey, which these are massive galaxies. And so after Chiles, these are the measurements that we have so far. These stars are stacked measurements that my colleague Nick Luber presented yesterday. And one of the things that he mentioned, he divides his stack into low mass and high stellar mass sample. And so one of the things that he mentioned yesterday was his high mass sample may show some evolution as a function of redshift. I don't know if you can even see it here, but there's a gray line that goes along this here, and this is our detection limit for Chiles. And so it may look like these points go up in redshift, but it really is due to the fact that our survey is flux limited. And so you can't really say anything about our points evolving with redshift because it's an H1 bias sample. So the plot I just showed you is this one in the middle, and I wanted to compare that with a plot of the stellar mass as a function of redshift and also H2 mass that we have. And so if you look at all of the galaxies above this yellow line, that's what I'm calling a higher mass sample, and it's the turquoise points and the orange points together. I'm not including the stacked points in the sample, but this is the high mass sample that I'll be comparing throughout the plots here. And you can see everything above 10 to the 10 stellar mass here. You can see progressively that the stellar mass across the board is higher, and then the H2 mass is a little bit lower than that. And then if you look at the H1 mass is lower, and then if you look at the H2 mass, that's even lower than the H1 mass. And so that's the trend that we see in the samples of high mass galaxies. And so it's not anything that's surprising. So this high stellar mass sample tends to lie higher on the star formation sequence. You can see up here, if you compare it to these high Z galaxies in the thicker turquoise and our points, our galaxies lie on the higher star formation sequence. And so what you can say is these galaxies have large reservoirs of H1, and they're actively feeding new star formation. And so the four galaxies in the sample have star formation rates of 3 to 30 solar masses per year. And so if we look at the gas fraction, this is H1 mass divided by stellar mass, and this is H2 mass divided by stellar mass as a function of redshift. The orange dashed line is a fit to that high stellar mass sample that I was pointing out. And we only have a few points, so I don't know how helpful it is to have a line fit to this, but it's just to try to show in general that the gas fraction for the H1 remains flat for this sample across redshift, and for the H2 it's relatively flat as well. And so I think this is, to me, one of the most interesting plots that I have on here. This is looking at the H2 divided by H1 gas fraction as a function of redshift. And this dotted gray line represents the 30% value at the local universe, which is this right here. And so if you look at the fit of this high stellar mass sample, you can see that it's relatively flat. I don't have the error bars in here, but it's pretty flat across redshift. So this fraction is not really changing with redshift. And so in summary, we're starting to fill in these points with a few measurements, and it's hard to say anything statistically about what we're seeing. But we can say, we have resolved images of the H1 gas, so we can say, what are these galaxies, what do they look like, and how do they compare with similar sample of galaxies at different lower redshift values, and so we can do that. So we resolve the gas, and we can look at the morphology of the gas and see if the gas is inside the galaxy or outside the galaxy at least, and see how that relates to the story of the evolution of individual galaxies. And with our JWST images, we can see that some of these systems have disturbed stellar components in addition to disturbed gas components. And we present 19 additional measurements for H1 and H2 past the local universe. And I think the takeaway at this point is that we do have an H1 biased result, and it shows that the cold gas content is predominantly H1, and that we don't see significant change in the H2 to H1 ratio taking place over the last 5 gigayears.
Thank you very much, Julia. I feel very lucky to be able to see finally H1 detections resolved, rotating at 0.5. That's spectacular. Thank you very much for showing it to us. Do we have questions, preferably from early career researchers? say your name, your university, your institutions. Don't be scared. Any questions? Martin?
Hi, thank you for the talk. Martin Bureau, University of Oxford. You stressed when you showed your H1 detection that, this was essentially a flux-limited sample, so you were very careful about what you said. But then you also stressed that the ratio of H1 to stellar mass and H1 to H2 were constant. But my question is, are these really reliable, given that you couldn't probably not have detected galaxies with lower H1 masses? So isn't it more likely you're just seeing the upper envelope of a distribution?
Yes, that is correct. And I think saying that the ratio is what we expected, it's really comparing it to samples like High-Z, which see similar results with their high mass galaxies. I think having so few data points and being flux limited, I think at this point it's we can really look at the stack detections like we're seeing in that my colleague presented yesterday, and really look at those in terms of whether or not we see real evolution as a function of redshift. I think looking at the stacked values is a little bit maybe more meaningful at this point.
Thank you very much, Julia, yet again. And our last speaker of the session is Henxing Pan, who will tell us about the fast survey of the cosmos field.
All right, thank you. First, I'd like to thank the organizer for inviting me to be here. My name is Henxing Pan. I'm from Oxford. I'm a postdoc right now. Today, I'd like to introduce a fast H1 survey over the cosmos field. Right, so first, it's just a little bit of background. Why do we want to do this? This is just our current view of the gas flow from the large structure to galaxy. First, we assume it will be in our atomic phase, then cool, condense to our molecular phase, and then further condense, and then trigger a star formation at the end. Or one of the major issues remains where these gas come from. This is the question we want to answer for our survey. If you zoom out of the galaxy, you can see the gas actually come from the so-called accretion gas. But these gas from this picture, you can imagine they must be cold, and there should be a certain fraction of atomic gas existing. So this will be a very important process for us to understand how the galaxy keep growing up. So how do we detect them? I think that's one of the questions we need to answer exactly. So this is a cartoon, shows like, let's say the galaxy exists in the center with the purple color indicating here, and surrounding by the CGM, and even further surrounding by the IGM. So how do we measure the trace IGM or CGM? And we could essentially trace it by observing the H1, because, like I said, there should be a certain fraction H1. If it's gas flow, then the principle here we're trying to adopt is that if we can measure the galaxy in the center, which we can do actually with the interferometer, like for instance the Mercator, because we know the interferometer are very sensitive to the point source, for example the distant galaxy. Then we could also do an image from a single-digit telescope, because we know single-digit telescope will be very sensitive to the Funda and extended structure. For single digit, we can cover the whole field. You see, now what you can do is try to quantify the difference between these two images. What's left should be the H1, remain in the CGM or IGM. If we can remove the H1 signal from the galaxy itself completely. I think this is the idea. So first, we want to detect the galaxy. So we yeah, I don't have to introduce too much about the Mercury telescope, but I just want to show this is pretty image. I think this 64 dishes in this area looks nice. I visited this place on last Sunday. I have to say it's as beautiful as it shows the dishes, except the weather is not quite similar. But we are radio astronomers, so we don't really care so much. So yeah, based on the Mercury telescope, we have this so-called MIGHTY survey. I think many people have heard about the MIGHTY survey, but I want to introduce a little bit further as a MIGHTY member. So we have this. This is the two fields. Actually, for MIGHTY, we have 4 fields will be covered. It is designed for studying the galaxy evolution by observing the 3 proofs, like continuum, spectral line, and polarization, led by Matt Jarvis and Russ Taylor. So this is the early science data. Here we only have 2 fields, but these 2 fields is essential for the reason you will see, because they are actually learn very close to the equator, so we'll be able to fast to observe as well. But for the former MIGHTY, we will have a much extended field to cover, even go to a different other even southern part of the sky. But the coverage and the depth will be much better than the early science data. So right now we have completed the data processing for the cosmos field. That is actually, we spend approximately 100 hours in this field, get very deep images, cover at least these 2 bands, the low frequency band, the middle frequency band over here. So yeah, it's in a 32K mode, so the data volume will be huge. For the visibility data, we have 500 terabytes, but the final product will be it's firmer than this actually. But if you want to check any papers, we do publish a few papers based on the early science data, at least a few over here that I was actively involved. We started, for instance, baryonic to relation, the H1 thermal relation, also H1 function. You can check out maybe later time. So then I want to introduce the FAST telescope. So this is another beautiful magnificent instrument. If you ever visit this place, you will see what I mean. Because if you purely perceive this telescope from this image, it might not look huge, right? It's just maybe a similar size with me. But if you actually visit the place, you will be just a pixel along this edge. It's just unbelievable. So yeah, and it's a very beautiful site. I mean, it's listed one of the top 10 tourist attraction places, actually. So I highly recommend people who have the chance to visit China to come take a look. The hotel are all very nice. It's unbelievable. Yeah. Right. So based on this telescope, we map the cosmos field, because, like I said, it's close to the equator, so it can be observed by both telescopes with quite a good amount of time. So we adopt the so-called on-the-fly mode observation to ensure uniform coverage of the full field. So yeah, we did actually, initially we spent 11 hours on this field, but then after a year we get extra 15 hours on this field. So in total, it's much larger than this field here. So the data processing, it's much simple than the interferometers. Because the only thing we need to care of here for the single dish is the continuum and the standing waves. So these are only 2 major issues, maybe including the alpha, yeah, maybe 3 major issues. So, but it's much simpler than the interferometer. So this is the waterfall plot. This is the time against the frequency. You can see the standing wave. It's with a period of about megahertz here. It's quite obvious. It's also background continuum, also strong RFI over here caused by satellites. We adopt the approach called the Fourier. It's a Fourier-based approach to remove the standing wave because it's like looks very stable. So we also remove the RFI like manually. So eventually the waterfall plot look like this. It's quite clean actually. So we based on all the waterfall plot data, then we form the H1 spectrum with a very deep sensitivity with the column density to 10 to the a few 17 actually. Here, so I want to introduce further about the source finding we did for this field exactly for our fast data. Here you can see basically nothing because why? Because I showed here it's a high pass survey. There actually for this particular field there's only one galaxy over here, which has already been also be observed by the fast. Then this was like 20 years ago, and after the 10 years, there was the alpha survey, right? They also covered basically the whole northern sky. So this the number of detections has increased up like on scale of 10. So then that is right now after another 10 years we have the fast survey. The number of detections has increased on a scale actually 100. Here I only list 80, but in fact there are quite a few other faint sources I couldn't see by eyeballing at the beginning, but later after we use the MIT data, we can actually locate them. They do exist. So it's on a scale over 100 detection over here. Then if we cross match our fast detection with the MIT detection on this picture, you can see most of them actually overlapped. There are fields not overlapped. Like I said, they are either very faint or very low velocity waves. But we do examine this, and they are faint indeed. Yeah. So I also cross match our detection with the optical surveys, like for instance here, Davis survey. We try to separate these detections into three categories. One is the so-called isolated H1 galaxy, denoted by the little dots. Another one will be H1 galaxy paired, because they located very closely on the fast image, and it's very hard to separate them. That's why I try to make sure classify these objects together as the galaxy paired. They showed here, but connected by this blue line. There are several, I think around 7 or 8. So we also find a few H1 gas group actually, at least 3 I spotted. But you can see that the fast H1 survey is very sensitive to the H1 content in the universe. So we did compare the fast H1 to the American H1 method. We find there is a 17% of fast H1 access for the isolated galaxy only. So it's not a lot, but there are still access. Then we also investigated the galaxy paired. The access is about 18%. It's much larger than for the isolated galaxy. It says like basically majority of the gas actually in ICM idea is associated with the interacting galactic system. The following is just some examples that I'm going to show. This is just one of the isolated galaxy. We have a 27% of H1 access. On the left, that's MIT image. You can see, you can trace the galaxy tail maybe over here, but it's on a very small scale compared to fast. Yeah. Which shows the high resolution of the Merkit over here. This is just one of the galaxy pairs. We do have the both images, the MIT and the fast, overlap together. We also discover H1 groups. Very nice, but we exclude them for analysis for now because they're quite complicated. We need a full source finding. Yeah, yeah, okay. We just sorry, yeah, 1 minute. We did compare the H1, the fast H1 and the mighty H1. We convert to the same resolution. We see the excess of H1 on scale of 1 megaparsec. It's not huge, but yeah, this is something we discovered quite interesting. But we will examine it further. Yeah. This is just the mighty H1 resolved images. There's some RAM pressure indicating because they are moving towards the group center. Okay, that's all. Thank you. I put my summary over here.
Thank you very much, Hinching. Apologies, we are running a little bit out of time. I see a question by early career researchers. I will only take those at this point. And you can always find Hinching and talk to him more about the fast survey of cosmos.
I'm Xu Lin from Peking University. I'm wondering what's the redshift range of the sources you detected with FAST, because in the introduction you mentioned that you want to detect extended fluxes with FAST, but Mighty H1 have the redshift from 0 to 0.6, but with FAST, the 3 Archimedes resolution, you could only resolve a 100 kbc disk at most to 100 megs per second, or a redshift of only 0.03. So what's your redshift range of your sources?
Okay, currently we only have the data processing for the L band. I think the redshift is up to 0.08, but there are data further than this, up to 0.6. You're right, but well, at the much higher redshift, the resolution is the issue, and the sensitivity is also an issue. In that case, we will do some stacking practice. I think kind of enhance our detection signal-to-noise ratio in total.
Let's thank Hinching again. And I remind everyone who is interested, who is part of SK H1 working group or not part, but would like to know more or join, we are having a meeting now here until 12:45. So please stay if you're interested. Otherwise, have a nice lunch. And please talk to all the speakers if you still have additional questions. And let's thank all the speakers of today.
15 minutes. Okay, yeah, that's good. Okay, in the interest of time, I think I'd like to get started with the penultimate session of Symposium 392. I'll be your chair this afternoon. I'm Sarah Blythe from the University of Cape Town, and we'll be starting off with an invited talk by Raffaella Morganti on H1 absorption and AGN feedback.
Thank you. Thanks for being here, and thanks for the invitation so I can update you a bit after all this emission, also about absorption. So I'm going to tell you about the associated absorption, so absorption that comes from gas in your target galaxy. And there will be 2 talks after me telling you a broader picture, a situation. Okay, so I've divided the talk in 2 parts, a bit of overview, just to bring you up to speed a bit, and then the part on the outflow, H1 outflow and the connection with feedback. So, okay, so H1 absorption is really a nice tracer for H1 because it takes you to higher redshift compared to the emission. And so, of course, it's not a perfect tracer, I'll see in a moment, but at least brings you to higher redshift because it works slightly different from the emission. It depends on the continuum, on the background continuum. As long as you have a background continuum, you can look at the presence of absorption. So you see here, to first order, the optical depths depend on the absorption depth and the continuum, the level of the continuum for a covering factor. So the real continuum that you have behind. Okay, so that's great because it takes you to higher redshift. Of course, as a limitation, you see only the gas that is in front of the continuum, of course. But it tells you about the evolution, or it can tell you about the evolution of the gas. And so the geometry is also clear. Whatever produce absorption has to be in front, the gas that produce absorption. And so most of the observation that I will show you come from provide you a profile, an absorption profile, as you will see in a moment. But in principle, you can go and resolve the distribution of the gas down to parsec scale. And I get to this, this is an example, I get to this at the end of the talk. So I will focus on AGN or radio galaxy in principle, but actually you can do absorption study on against everything as long as there is a continuum. So a galaxy like NGC 6946, a nice spiral presented many times, has also an absorption. So keep an eye on that. Okay, so what we do, what we have done so far are mostly pointed observations. So the result that I will show comes mostly from pointed observation, small survey, but and most of the work is done at lower redshift. But we are getting to the stage in which the blind survey are starting, and those are very, very important. And they already show some very intriguing results. So I listed here the main, like ASCAP flash, that will be the topic of the next talk, or one of the next, that indeed is a dedicated H1 absorption survey. But try have been done also with FAST, drift scan, or Meerkat MALS that Neeraj will tell you. But actually you can do H1 absorption on every field that you observe with a broad enough band. And so you can look for absorption inside your area. So that's also is happening. Okay, I could not resist to show one of these spectrum from FLASH. that I'm sure will be discussed more, but this is a spectrum from 0.4, redshift 0.4 to redshift 1 that you get at the location of one of the continuum sources. For every continuum source in your field, you can get a spectrum like this. And interestingly, here you have an absorption, and I'll get to that later on. So what kind of structure you trace, because that's what we actually want to know. Usually the absorption is against the core, the central region of your galaxy, but there are exceptions that are becoming a bit more common, I would not say, but we have a few of them. So here you see, and I just wanted to show you one, just as a warning also. Here you see a radio galaxy with the core and 2 lobes. And here you see an H1 absorption that we just obtained with Meerkat. We were very happy about the H1 absorption, but in fact, the absorption comes from this galaxy that happens to be in front of one of the radio lobes. So this absorption has a difference of about 1800 kilometers per second compared to the systemic velocity of this. So in a way, it's an intruder. But cases like this have been found, and so my feeling is, as the survey will expand, there are more and more of this situation where we have essentially tracing also the environment of a galaxy. So this is important. It's important to note here that the resolution of your continuum, to know about the resolution of your continuum, not just have a blob, this is Meerkat, so it's about 8 arcseconds, is very important to disentangle what you are looking at. But usually what you see are structural or circumnuclear disk, outflow, I'll get to that at the end, and also inflowing gas. The trick here is that this structure may coexist in your profile. So here you see a profile, an absorption profile, where this deep part is associated with this circumnuclear disk, while this very broad, many hundred kilometers per second, is an outflow. It's blue shifted and is an outflow. So disentangling this structure is also tricky. And again, knowing about the structure of your continuum, that provide the screen is very important. So absorption is great, but you also need good ancillary data to fill and to complete the picture. Okay, oops, this was not supposed to be here, but okay. Okay, so let me tell you about the occurrence of this H1 absorption. So just quickly, at low redshift, we have done many studies, so we can do some statistics. And what you see here, we have optical depth that are the one that also set the noise that you want to reach in your observation, between a few percent and 15%, sometimes even higher, but are rare. Very likely there are also lower optical depths, as I will show you, but just the depth of our observation don't allow us to see them. There is not much dependence, at least at the moment, with the luminosity or the redshift, at least a low redshift. But interestingly, and very important for the AGN feedback, I'll get to that later, compact peak spectrum sources are the one where more often H1 absorption is found. And compact peak spectrum, you see here an example that is actually the source in the flash spectrum I showed you before. Peak spectrum is an indication of synchrotron self-absorption, so young sources where the jet is just expanding as we speak. So these are very, very commonly seen. We have about 25% detection rate, and this holds also at high redshift. And this is interesting. I'll get back in a moment. So these are nice objects where the effect of the jet really has impact, and so very interesting. For the extended sources where the jet are already many kiloparsecs, the situation is a bit more confused. The detection rate is lower, and what we still don't know, at least I don't know, is whether there is any bias in the observation that we do. And as example, I would like to show you this to remind you how important it is to know the background that allow the absorption. So here you see two objects. This is these two radio galaxies from sample that we have studied at 6 arc-second resolution, so it's not even so bad. But then when you go to 0.8, you see this has a very strong core. So this is a good candidate. This I can try to detect H1 absorption. This one turned out to have a very weak core. So even if my observation H1 absorption are at this resolution, I know that against this core, very unlikely I will find H1 absorption, unless I go super deep. It's only 9 millijansky, this core. So it's a warning that I'll give, because knowing what is behind, what is at high resolution, is actually what determines whether you can detect or not H1 absorption. So just keep an eye on that. Okay, the high redshift is the one at this stage very interesting, and is one where the new survey really should make the difference. And at the moment we have confusing result. So let me mention this. We have a much lower detection rate. Higher redshift, I mean above 0.4, is, well, can change. We have a lower detection rate, and we don't know exactly whether it is due to some bias or to the condition of the environment, the universe in general, that change the probability to detect H1 absorption. So as you can imagine, this is a key question that we really want to address. And so let me explain a little bit here. So first of all, at higher redshift, so you see here a distribution of the radio power as a function of redshift up to 1. And so you see at low redshift, so in this region, we trace or we look for H1 absorption in low power and in relatively high power radio galaxy or radio source, while at high redshift we only sample the high power jet and sources. So we are looking at different objects, and this is something that we need to take into account when we do statistics. And this is, we still don't know, because these objects tend to have a very weak core. So the bias that I mentioned before enter the discussion. Okay, this is a possibility, but the other possibility is that UV luminosity is actually higher at higher redshift for these sources, so they should ionize the gas instead of seeing H1. A sample of galaxy done that you see summarized here with the UV luminosity plotted here, show that you have detection and non-detection, detection at the red and detection at the blue, non-detection at the red, also for low UV luminosity. So that doesn't seem to be the parameter that change. It could be that the condition of the H1 are really different, low column density or high spin temperature, whatever. And really, this is a key question that we need to address now, and we can do with the new survey, especially FLASH and MULS. So that's very exciting, and the new frontier, I would say. So this was the general introduction. I want to spend the last few minutes, on the outflow, because of course for cold gas like the H1, you would not have expected to see the gas outflowing at many hundred kilometers per second, up to 1,000 kilometers per second from the galaxy. Too much energetic process to keep the H1, but this is actually something found, and after the H1, even the molecular gas trace this outflow. So that's important for the feedback. I'll get to that. So I wanted to show you the first object where we have detected this outflow, because I still find this very cool, and is one of the only object where I can show you, one of the few objects where I can show you absorption and emission in the same plot. So is this S0 galaxy. that has a disk of H1 in emission, has a radio source in the center, is a Seyfert galaxy, by the way, and this is a position velocity along this axis, the radio axis. And so you see the rotation that you know all about by now, the rotation of the H1 emission, and here the absorption. So you see that the gas associated with the absorption, so in front of your radio source, has really a kinematic that has nothing to do with the rotation. This is a wonderful example because you can compare the two directly. So this was, of course, a surprising result, but by now we know many objects, and as I say, we also know objects in cold molecular gas. ALMA has done a lot of work on this. So interestingly, we find this outflow very common in young peaked radio source, the one that I mentioned you before. So there is where the jet is young, is getting out of the central dense part, and so that has implication for the impact of the AGN and in particular the jet on the medium. So this outflow are typically very shallow in optical depth, and so this creates an extra complication. And I wanted to show you this example from Meerkat as a requirement, let's say, for what we want to achieve. This is an absorption against a source of 5 Jansky. It's only 0.1% optical depth, and we can trust this absorption that is all blue shifted because the band pass is really stable during the observation. So we can trust that any shallow component is real. And so that's really great. This is what we want to have in all the observation. So here are some examples from work collected from different telescopes, as you can see, collected through the years. And just to tell you, the importance of this outflow is that they carry most of the mass, much higher than what the warm ionized gas does. So the H1 and the molecular are the most massive outflow. We have outflow rate between 1 and few tenths of solar masses per year, and they must be associated with fast cooling of the medium, otherwise you will not see H1. Identify the location is key for this, to know really what they do. And so I want to show you 2 examples. This is now I'm switching to the VLBI, so I'm going to look in detail at the continuum, resolve the continuum, background continuum, and see where the gas is, the absorption gas is. So this is the integrated profile, like I showed before, but these are image of the outflowing gas and the regularly rotating gas that is associated with the disk, we know. And as you can see, the outflowing gas breaks down in clouds that are outflowing with many hundred kilometers per second, about 600. And so these are clouds of about 40 parsec flowing out and with a mass about 10 to the 4, 10 to the 5 solar masses. So what this is telling us is that actually the simulation that people are doing now about the jet entering a clumpy medium and impacting and producing feedback are okay, are correct in the sense that we see the clumpy medium. We see the clumpy medium in H1. So these are the the cloud that survived the impact of the jet. But the simulation don't only talk about outflow, they also talk about cocoon of gas, of shock gas that expand into the medium. So there is more than the jet can do, not just the direct impact on each cloud that encounter. And so this is something that instead we can see in the turbulence of the gas. And this is another VLBI observation at 4 parsec resolution. So I think this is really amazing what you can do. So I really hope the VLBI will take up and have a component in SK. So this is a radio galaxy here of 100 parsec in total, where we see an outflow at about 30 parsec from the center. Okay, so that's part of the feedback, but we also see the entire H1 absorption having a high velocity dispersion. So we think this is the impact of the jet in the disk when they expand and as effect increase the turbulence of the gas. That we think could have implication for the star formation, but that's the next step to explore. So H1 take us, I'm done. H1 take us to the region where there is a continuum, as I say at the beginning, of course, to go a step further to really see what the jet can do at a larger distance. We need the emission. And so this is a nice synergy with ALMA and with NOEMA to see what the gas does at larger distance. So I have my summary here. Just one small comment is that the H1 absorption has then this very high synergy with the continuum, much more than the H1 emission that we have seen this. So there is really a strong link, and with the cold molecular gas. So a lot of fun. Thank you.
Thank you very much. Are there any questions, particularly from early career researchers? First. And just a reminder, please, can you just state your name and affiliation before you ask the question?
Thank you very much for your talk. My name is Tanita Ramvirth-Hut. I'm a PhD student at the University of Geneva. And I work on studying gas and galaxies with optical and UV spectroscopy. And I was wondering if there's been any kind of synergies between, I think I asked a similar question earlier this week, but synergies between H1 absorption and like metallicity from UV.
All the objects that we have studied have also the study of the warm ionized gas. So you can trace it. Usually they have also outflow. They have disturbed kinematic. The mass outflow rate is not so large. So this is why the cold gas is interesting. And you don't get to this few parsec scale, as I show you in the VLBI, that I think is really, really cool.
Do we have any online questions? Time for one more.
Ciao Raffaella, Luca Cortese di Craigidable. That's beautiful stuff. Just a curiosity, these are all AGN-driven outflows because you need a strong continuum source. So I was wondering, what are the prospects to push this to fainter radio continuum sources and look for star formation-driven outflows?
Yeah, these are all in early type with not much star formation. So yeah, we tend to stay away from star formation, but nobody prevent to, as I say, essentially it's a matter of the continuum, the background continuum. So could be done. Maybe choose the right object. I don't know. Okay.
Right, I think that's all we have time for now. Thanks very much.
Yeah.
Our next speaker will be Neeraj Gupta, who is a remote speaker. So if we could get Neeraj online. And he will be talking to us about MULS, the MULS survey.
Is my screen visible?
We can see you, not your slides yet.
Now?
Yes. Great. Go ahead, Neeraj.
Okay, perfect. Thanks, Sarah. And thanks, Raffaella, for excellent introduction to absorption line science. I'll focus on meerkat absorption line survey. Specifically, I'll talk about absorbers at redshift less than 0.6. And I'll first start with acknowledgement to the whole collaboration that has contributed to this survey. And there has already been a number of excellent talks already describing that why we need to really understand how the cold gas phase of neutral hydrogen is evolving if we really want to understand how gas goes into star formation. And this is one of the primary objectives of MALS, which is to use 21 centimeter absorption line because it has this inverse dependence on temperature that allows us to explore the thermal state of the gas. And for MALS, we are using two receivers of Meerkat. One is at L band, another is UHF band. And L band, which is what I'm going to focus today, goes from 900 to 1670 megahertz, which means redshift of 0 to 0.6. And of course, we can also observe OH in this redshift range, but I'm not going to cover that. But I think we should all keep this in mind that with the sensitivity of precursors, OH is now accessible. With SK, it will become really practically possible. And that will also give a very good connection to how H2 is present in the diffuse ISM. Now, coming back to MALS's status, we have finished L-band phase, which involved 400 pointings, and that's what I'm describing today. And for UHF, we are more than halfway complete, and we are observing 400 pointings at both the bands. And let me first start by describing where and how MALS is looking at the sky. So as I said, we are observing approximately 400 pointings at L and UHF band. And this on the left-hand side of the screen, we are looking at one typical MALS pointing at L band. And this is like 3-degree extent. So we go well beyond FWHM. And there are approximately 400,000 sources per pointing. So which means that if you put together entire 400 pointings, we get about few million sources, which are both AGN and star-forming galaxies over about a kilodegree square. And with the sensitivity, spectral line sensitivity that is available to MALS, then we can actually optimistically look for absorption towards any source which is brighter than 1 millijansky. So that's pretty much all AGN we are looking at. If you want to look at star-forming galaxies in particular, we need to sort of integrate much more so that we can look at fainter sources. On right-hand side, we have a median RMS map that is coming out of all the pointing. So naturally, we see that like the RMS increasing as we go away from the pointing center. But as far as absorption is concerned, what we are concerned with is a bright source. Doesn't matter where it is in the pointing. And so at any point of time, there are about a couple of hundred sources within MALS pointing, which are interesting to look for absorption. And that's something what we are trying to focus on in MALS. And so each spectra or each continuum source that we have in MALS pointing produces a spectra like this. This is our first spectrum that we took at both L and UHF band. And you can see from the top left corner, it starts from 560 megahertz, which is coming from UHF band. That's the first panel here. And then the second and third panels cover L band, which is going from 870 megahertz to approximately 1700 megahertz. And we can see there are a lot of nice absorption features detected here. And bandpass, as Rafaela described from Meerkat, is very, very stable. But then there are also these patches we see in between, which are affected by RFI. So that's one of the major challenges that we need to tackle when we are doing these blind surveys. So with these kind of spectra produced for like few hundred sources within pointing, we can do a lot of nice blind searches for H1 and OH. And this is how MALS footprint is spread over the sky. There are approximately 600 pointings we selected, of which we are observing 400 at both L and UHF. And since we are interested in looking at cold phase of H1, we would naturally like to have good redshifts for as many objects as possible, because to first order, it allows us to separate which one is intervening and which one is associated absorption. But also, like if we can detect all the other lines, like in case of AGN, we can classify AGN into different excitation schemes, like high excitation or low excitation radio galaxy, or in case of intervening absorbers, we can look at other tracers like metal absorption lines or of magnesium 2 or carbon and other things. Then we can also constrain metallicity and dust in these absorbers. And all of these are really important to really understand what we are detecting from the survey. And since these are large number of objects involved here, we have like ongoing partnership with large optical surveys so that we can accumulate as many of these possible. So this is one aspect to keep in mind. Now with this, I want to focus quickly on two aspects of L-band science. One is like MALS H1 absorber at Z equals to 0 itself, that is within our galaxy. And why this is important, because like a large amount of information that we have about neutral ISM comes from our understanding of Milky Way. And as Rafaela was describing, that if you want to interpret absorbers or extragalactic absorbers correctly, we need to understand at what physical scale such absorption lines are produced, and what maybe their optical depth distribution, also in what kind of physical conditions we expect to see 21 centimeter absorption. And there is no other place like our galaxy. And each sightline that is there in Mars also passes through the Milky Way environment. So what we see here on the top left corner of here is the Milky Way H1 emission, and on top of these, each point here represents Mars pointing. And the blue ones are where there is at least one absorption line detected from in the Mars pointing, and the red ones are those where none are detected. And you can see that there is reasonable correlation with where we see more H1 emission and there are detections, and where there is much less H1 emission, there is much less detection. So there are about 20,000 sightlines which like this in Mars catalog, which are brighter than 1 millijansky. And if we run this through automated absorption line search, we produce something like 3,500 detections. And some of those are shown in the top right panel here. You can see that variety of structure, but about 80% of these are actually can be fitted with single Gaussian components. So they're fairly simple as far as our galaxy is concerned. So now there are three nice proof of concepts. These are observational properties that are coming out from this search, but also applicable to extragalactic search in terms of interpretation, also like how well we are doing in terms of methods. So on the left-hand side at the bottom, what we are seeing is x-axis is the distance from the pointing center. And the big histogram in cyan is showing all the sightlines distribution for them. And the hashed one is actually showing the ones which are detections. So as we have been emphasizing, that this absorption can be detected anywhere in the pointing. But what matters for absorption is actually not just where the source is, but what is the optical depth sensitivity that it provides. And that's what is shown in the second panel. X-axis here is optical depth sensitivity, and we can see that like at the highest end, we can detect approximately 85% is detection. So at the extreme left, we have like about 400 sightlines with optical depth sensitivity of approximately peak optical depth sensitivity of 0.05, and then these are in 90% of these absorption is detected. And as we move towards the right-hand side, the detection falls off to something like 10%. And extreme right, what we are seeing is a distribution of peak optical depth, peak SNR rather here. But it's a reasonably good metric in this case, because most of the absorption is defined by a single component. And what we are seeing here is that for anything more than peak SNR greater than 6, the absorption is very well defined. It's also visually confirmed. But when we are talking about lower signal to noise, then only 50% of them get visually confirmed. And most of the absorption that we're detecting in this case in the LSR frame have velocity less than 50 kilometers per second. And that is not surprising, because here we are mostly covering high latitude range. So most of the absorption that we are seeing is coming from the local interstellar medium. So this is very nice to be able to define that where the absorption is produced, because then we know that what kind of metallicities and radiation field it may be exposed to. And that's something what I try to summarize here in the bottom two panels here. On the left-hand side, again, I'm showing, if you recall, these two different sets of pointings, the blue ones where some absorption is detected, and then the red and cyan ones are where none is detected. X-axis in the bottom left panel is actually the visual extinction. And you can see that there is a reasonable segregation between the two, not complete, but it's nice. So it's a framework in which we can now explain what we are seeing. And on the right-hand side, what we are seeing here is that within per pointing, since there are multiple sightlines, we can actually estimate what is the difference in the optical depth. That is the optical depth fluctuation that we are seeing within the beam. And on x-axis is actually the parsec scale separation. So what we are seeing here is actually how the optical depth scatter is there per pointing as a function of the physical separation between these sightlines. And this is a very nice property of which can be used to interpret what kind of structures that we are seeing in the ISM and what kind of turbulence properties that it may relate to. I cannot go into more details of it, but I just want to cycle back to the initial statements that I made, and then Rafaela was describing that we would really like to know if the physical environment and the length scales over which these absorptions are produced. So these are some of the questions that can actually be answered from galactic science as well. Now moving towards the extragalactic side of things. So with this understanding and confidence, what do we see actually if we apply it to extragalactic spectra? So now we have this spectra covering 900 to 1420 megahertz approximately, and then what we are seeing in the left panel here is actually like what kind of different candidates that we detect from these 20,000 sightlines. But in this case, now they are brighter than 4 millijansky because we define continuum sensitivity at the lower end of the frequency band. So the sources are brighter because of the steeper spectral index. And there are 100 plus detections that we get from this. Some are associated, some are intervening. We are still working on this segregation. You can see some of the profiles here. Some are very narrow, some are very broad. So much more variety in this case compared to what we were able to detect in galactic scenario. So that's in progress, but we think that we have got enough detections here that we can constrain CNM covering factor of gas in galaxies over this redshift range at the accuracy of 10 to 20%. That was kind of initial goal of the survey. So we are getting ballpark into that number. We have to still do some completeness analysis, but we are getting close to it. Now, this is on the right-hand side is another plot, which is now focusing only on the associated absorbers. So there are these two curves actually in this. They represent the luminosity that is accessible to MALS, and various colored points are actually observation that has preceded MALS coming from the literature. And the pluses that we are seeing here in redshift range 0.2 to 0.6 is the sample that is Partha Deka, PhD student at IAU GA, is working on. And these are a sample of high excitation and low excitation radio galaxy. And you can see that with MALS, due to high sensitivity, we are now able to access to the low luminosity regime, which was not previously accessible. And this is another point that Rafaela was emphasizing, that with these new surveys, we are actually breaking ground into the new population of radio sources, but in a very unbiased way. I think that is the advantage, because none of these have been selected on the basis of any optical information. But of course, after we observe them, we have to look for optical spectra if you want, in some sense, if you want to classify them, classify their AGN properties. So this is the status of what is going on with the H1 absorption science with L-band. I want to now quickly, over next 2-3 slides, tell you what is the status of our data releases so that you can utilize some of this data, continuum as well as spectral lines. So last year, 2023, we actually released continuum catalog. This is the baseline catalog for all our absorption line science, 500,000 sources detected with all the spectral indices and all the information. So that is already available. Next week, second data release. Yeah,
we're into question time. So if you could.
Okay, okay. Sorry, I was not able to see this. I'm sorry about that. So the second data release from the continuum is coming next week, and then I move, and all this accessible from our website. And this is my summary slide. These are, in addition to survey science, there's a lot of detailed studies of individual objects also possible, which I have showcased here. Please feel free to visit our website, look at these, explore data. And this is where I stop. Thanks a lot. I'm sorry about a couple of minutes that I've delayed into.
Thanks so much, Neeraj. Do we have any questions in the room?
Just to be clear. Hi, Neeraj, Betsy.
Hey.
Very great talk. Very cool to see the data releases. I was impressed by how narrow some of your absorption profiles were for the extragalactic. Is that physical? Like, do you really, like, is that the gas is really that cold?
So the resolution is 5.6 kilometers per second, and with GMRT, when we were able to observe with, like, let's say 1 kilometer per second targeted searches, we have detected in some cases absorbers which are like 3 to 4 kilometers per second width in intervening cases. Yes, because for CNM, if we just take theoretical temperature 100 Kelvin, it will give 2 kilometers per second. So 4 to 5 kilometers per second can be detected in some cases. Yeah.
I think we'll have to stop there. Thanks so much. And perhaps if anyone has other questions, it could go on the Slack. Our next speaker will be Hein Yoon, talking to us about ASCAP Flash research highlights.
Oh, good. The previous, yes. I'm Hee Nhu from Seoul National University. So I'll be talking about another H1 absorption talk, talking about SCAP Flash on behalf of the team. So, right. So first, thanks organizer to have to give me the opportunity to present this work, and also thanks IAU for the travel support to allow me come here. So the results presented in this talk actually are submitted to PASA, and you can also get the manuscript from the archives. So please use this QR code and see the exciting result from the FLASH team. And this talk, this result has been made by a huge number of people listed here, and some are in the room, so I appreciate the team. So this is the after lunch talk, so I will just draw some attention with just starting with the conclusion slide. So in summary, we detected 30 new H1 absorptions. So as Rafaela mentioned, considering the total number of the absorption studied to date, like 200 or so, it is a great achievement. And another thing is the first survey is ongoing, so we will find many more. So the expectation is a few hundred for the entire first survey period. So to give you more details, so FLASH is one of the 9 SCAP survey science projects. So spectral line data, spectral line project, along with Wallaby and Dingo and GasCap. So PI is Elaine Sadler and Liz Mahoney. And this is a large area H1 21 centimeter absorption line survey using background radio sources. So the little bit different from the Mars survey presented previously, it is a non-optical pre-selection target survey. So basically, we don't know actually the optical counterpart, so any counterpart. So basically, we just extract all the spectrum toward the radio sources in the field. So to give you a rough number is we have some kind of 500 to 600 spectra per each field, and we will be targeting 600 fields. So in total, roughly 400,000 spectra will be extracted, and that is a combination of the meaningful spectra and some kind of just flex spectra. So the main thing we have to do is just finding meaningful H1 absorption from the spectra. So the motivation is to understand the H1 content of the galaxies or radio sources over the cosmic time. So our redshift range is from 0.4 to 1. So the loopback time is correspond to 4 to 8 giga-year. So the survey description paper is led by James Allison. So you can get more details. And the red box in the right-hand side is the window we like to observe. So FLASH pilot surveys have been successfully done in 2022. So footprint is 92, and just excluding some repeat field and some kind of duplicated fields, we have 77 in total. So that covers 3,000 square sub-degrees. So the frequency range is from 711 to almost 1,000, and the rest range is from 0.2 to 1, and it covers almost the entire southern sky and some part of the northern sky. And the field of view is 6 by 6 square degrees. So most of the field will be observed in 2 hours, and 6 hours some kind of test fields. So we will stick to 2 hours for the first survey. So this is a typical and good example of the data product from the pilot survey. So on your left-hand side, you can see the good quality of the continuing images, and it shows the strength of the SCAP survey has a large field of view. And on your right-hand side, you already saw this the clear large bandwidth covered almost 300 megahertz. And RMS noise is roughly 90 microjansky for the continuum images, and spectra we have 5 millijansky for the 2 hours observations. If there is some kind of meaningful absorption, you can make some kind of zoom in image like this. So it is one example of the intervening absorption at redshift 0.7. So there are several challenges in the beginning of the pilot survey. Now we have fixed most of the issues, so I don't give too much details on that. If you're interested in, just revisit my recorded talk for the focus meeting 5. And the biggest challenge at the moment for the first survey is a bit of solar interference and tropospheric ducting. But there is some kind of great improvement by operation teams. So we have some kind of ducting monitors. So we try to stop the observations in the beginning of the observation without any loss of the observation. So there are some kind of improvement for the rest of the first survey observation. So the next thing we have to do is, after extracting the spectra, we have to find the meaningful detection from the scratch. So what we do is using Flash Finder developed by James Allison. So it is basically Bayesian line searching tool. So we assume some kind of single Gaussian line first, and then if we find any feature, then we try to fit like multiple component or some other clues, and then identify some kind of meaningful absorption. So you can see the completeness of the line finding search from on your left-hand side. And at the given signal-to-noise ratio, you can see the good completeness. But for the narrow feature, compared to the broader feature, it is not easy to get from the given data. So I will discuss it later. And this is the summary plot of the H-on line properties, peak optical depth and line width as a function of the continuum flux density. So on your left-hand side, you can see the limitation of the optical depth is higher when flux is fainter. So this is the basic idea. We use absorption. Absorption, which is only sensitive to the flux density of the background continuum source. And good thing is here, the diagonal line is actually the prediction from the James Allison even before we start this survey a decade ago, but we can see we reached the sensitivity with the actual data, so this is very good sign. And on your right-hand side, you can see the distribution of the line width as a function of flux density. So it covers from the narrow to broad line. But here we notice that some kind of very narrow feature under 20 kilometers per second in line is we can't get that kind of very narrow intervening sources. So we will just carefully have a look at this kind of issues for the rest of the first survey observation. So after finding the meaningful absorption, what we have to do is to understand the origin of the absorption. So one is associated one, and the other one is intervening observer. So the best thing is if we have some kind of optical spectroscopy data to get the redshift information and find the optical counterpart, that is the best. But for this kind of untargeted survey, it is not very easy to get kind of uniform, consistent spectroscopy data. So what we try to do is, given the known H-on absorption, we train that as a model set and then try to identify them based on a logistic regression method. So what we did is, this is preliminary results. So among the 30 detection, we identified 16 as intervening and 14 as associated based on this kind of machine learning trials. So it doesn't give very absolute solution, but it gives very great insight to understand the origin of each observer. And we will increase our sample as ongoing first survey progress, and then we can increase the model set, and we expect some kind of a high accuracy of the prediction by this method. So this is examples of the one associated and intervening, and it's at the left-hand side. You can see the MRC source is already published by Auditorium, and this is the one of the highest optical depth integrated velocity optical depth source. This is a good candidate of the H associated observer, and it is known as a peaked spectrum radius source and huge optical depth, integrated optical depth, and high column density. And on your right-hand side, the biggest difference between the associated and intervening so far is the line width. That is the main thing when we run the machine learning or when we do some kind of multi-wavelength studies to collect the data and identify each each line. The Linus is the biggest tracer to identify its origin of the line. So on your right-hand side, you can see the example of intervening, and we can't see any optical counterpart from this source and very narrow line feature. And there are some Meerkat follow observations led by Liz Mauney and Marcin Glowacki. And then we saw with the great sensitivity of the Meerkat, the feature is actually consistent with the ASCAP observation. So this is a strong candidate of intervening observer. All right. So given the results, we try to discuss the H1 detection rate at this threshold range. So from the pilot one, we found 17 new lines out of 37 field, and pilot two, we got 12. So for the pilot one, we got detection rate like 0.46, and pilot two, 0.32. We think this difference is mainly due to some wobble feature from the pilot 2, so we will stick to the number from pilot 1 as an indicator of the first survey detection rate. But what we actually think originally thought the expected detection rate is roughly 3.1, but if we assume only line is above 20 kilometers per second, it could be 1.1 line per field. So we think about that kind of some possibility. There are many possibilities, but we did some tests with the gamma field and MRC field based on the optically selected sources. And then we studied the actual detection rate with combining the flash data. So, and then we found 3% of detection from the gamma field and only 2% of detection from the MRC field. So the actual detection rate could be lower than actual the previous expectation. And another thing is, as I showed you, we missed some kind of very narrow feature for the intervening sources. So this kind of discrepancy can contribute this kind of lower detection rate, but we will figure out with the first survey data. Okay, so I'm almost end. So this is the status of the first survey. So we already observed and released 136 fields. It is more than actually pilot field. And you can get the data from the CASTA, and it is 23% achieved. So we are on the right track to finish within the 5 years. And this is really right final slide. So it is the last day of the meeting, but there are plenty of flash talk or indirect talk with the flash data. So if you have any chance, just revisit some of the recorded talk from the YouTube. And there are many upcoming data, for example, like optical counterpart. So please stay tuned for the more exciting data, exciting results with the first survey data. Yes, I will stop here.
Thanks very much, Hein. Any questions? We've got time, I think, for one. Oh, there's one at the back. Mario's making me run. Oh, thanks, Nazir.
Well, okay, actually, I didn't want to be the only question because it's more technical, not related with the science here, which is that I might have missed, but the first slide you mentioned, like you solved several issues. One of them was the sun, solar contamination. How did you solve that one?
Actually, it is not easy to fix that. The best thing is avoid that time. But we just figure out some kind of solar interference and some kind of influence as a function of time. And it is strongly affected only sunrise and sunset time so far for the flash data. So we try to avoid that. Yeah.
Thanks very much. I think we'd better move on with the next talk. Our next speaker will be Luca Cortesis, talking to us about the physical connection between angular momentum and cold gas.
Thanks a lot, Sarah. Good afternoon, everybody. So now we are switching back to H1 in emission, and what I'm going to present to you is actually work that was done by Jennifer Hardwick as part of her PhD thesis at IAU GA. Let's see when the slides come up. Yeah, so that's my intro slide. So this was a movie supposed to work, but just to give you the idea and remind us that when we think that gas accretes into galaxies, it should bring angular momentum to the disk. So the idea is that somehow the angular momentum of the baryon component in galaxies and the H1 component should talk to each other. And indeed, this was something at the basis of some of the early semianalytic works. You can see this on the left. This is now almost 3 decades old, where you see the relation between gas fraction and circular velocity of galaxies. You see the so-called gas fraction stellar mass relation, but the scatter is primarily driven by the spin parameter of the halo. This makes sense, and curiously, in the last decade, there has been a second youth in this kind of idea of stability modeling disks. They have been developed by different groups and reaching the conclusion that sometimes it could be that the angular momentum of galaxies is the only and primary regulator of the H1 component in disks. This has been reframed very recently by Pavel in trying to look at the scatter in the baryonic mass and baryonic specific angular momentum of galaxies and try to see whether the scattering in the relation is only and just driven by the atomic gas fraction in galaxies. So the challenge observation is that most of these works were focusing and were based on what we generally call the H1 selected samples. So looking simply at the tip of the iceberg of the galaxy population. And so what we wanted to do is to expand this to a sample that is more representative of the local universe to figure out whether really the connection between H1 content and angular momentum is so simple, or primarily whether H1 really just care about the angular momentum of the entire baryonic component. So to do this, what we used is that we combined the X-gas and the X-cold gas samples. These are samples that have already been introduced. The take-home message here, or something, the only thing to remind you about these samples is that these go to significantly lower gas fraction, so they allow than the H1 selected samples, so they allow us to probe a more representative sample across a 10 to the 9 to 10 to the 11 stellar masses. Of course, this comes from single-dish data. So you might ask, why the hell do I use single-dish data to do specific angular momentum? And this has been our challenge to start with. But it's something that it's worth investigating, because even with the SKA, and at least with ASCAP and Meerkat, when we go in particular to iRedshift, most of the sources will be barely resolved or unresolved. So it's very interesting to try to figure out how much we can push this. Unfortunately, I don't have time to go through the technique, but the take-home message here is that if you have good detections in H1, you have good estimate of the W50 or the velocity width, and then you combine this with multi-wavelength data, in particular optical imaging that allows you to reconstruct a careful stellar mass surface density profile, you can actually determine a specific angular momentum of the various baryonic components with an uncertainty that it's less than 0.1 dex, and the 0.1 dex only starts when you get to the very low mass regime, where the shape of the rotation curve is much more uncertain. So with this in mind, what we started doing is just to check that we were in line with previous analysis of the stellar mass versus stellar specific angular momentum compared to what done by resolved studies. And here what you see in the 2 left-hand panels, on the top you see the global relation when we look at the entire stellar component of galaxies, when in the bottom panel you see the relation only for the disk. This is just to check that everything was making sense and does make sense. Much more interesting is the colored panels on the right. Here you see a first investigation of what might drive physically the scatter in these relations. You see 3 columns, bulge to total ratio on the left, H1 gas fraction on the middle, and specific star formation rate to the right. The top row shows you the scatter for the entire sample, while the middle and bottom row show you the scatter for only low mass and high mass galaxies. And you can see already from here that when we look at the whole sample, most of the scatter seems to correlate with H1 gas fraction, as expected.
by the simple stability argument. But when we split the sample in terms of stellar masses, you see that when we go at high stellar masses, the trend with a gas fraction seems to become significantly weaker, if existent, frankly. And if there is a trend, it seems to be more evident with what we would naively call a stellar structure, Barge to total ratio. But this is not what we wanted to look at. We wanted really to look at the entire baryonic information of galaxies and reframing this in this parameter space that I've introduced you at the beginning. So we have baryonic mass in the x-axis. Here by baryonic I mean stars, H1, H2, and a correction for helium, and the baryonic specific angular momentum on the y-axis. Here you have 4 different panels for 4 different ranges of gas fraction, from high gas fraction to the right and lower gas fraction moving to the left. The colored points are the X-gas galaxies, while the colored bands show you what you would expect for the simple argument that the H1 is just regulated by the stability of the disk and the kinematic of the disks. So that H1 only cares about the angular momentum of the baryonic component. You see that when we are to the right-hand panel, so we are in disks where a good fraction of the baryonic component is dominated by the H1, the two agree reasonably well. The more we move towards the left, so the less H1-rich galaxies become, the more is the deviation between the points and this assumption. So telling us that when we go to a galaxy more normal, like our own Milky Way, or even galaxies that are less gas-rich than our own Milky Way, this physical connection between H1 and angular momentum might be a little bit more complicated. Of course, there are a lot of challenges here because we are using X-gas. It might not be ideal. So the next step that we did is to try to compare it also with radiodynamical cosmological simulations. And what we did is we used both the Lastris and the Eagle runs to extract X-gas mock samples. Pretty much we use the same stellar mass selection in X-gas, we use the same gas fraction selection limit, and then we reproduce the stellar mass distribution of X-gas simply because X-gas was set to have a flat-ish stellar mass distribution. And so when we do this, we can go back to this parameter space. Now, the only difference that I've done here, I've removed, for simplicity, the X-gas points. I'm just showing the 2 black lines show you the 2 ranges covered by X-gas in each panel of gas fraction. And here the teal line shows you Eagle and the median relation for that bin of gas fraction, and the mauve line shows you Lastris TNG. You see that at face value, there is quite remarkable agreement between the 2 simulations, which is not necessarily by construction, and also with X-gas. So the other important thing to focus, if you look at the plot on the right, this is the scatter across the plane, this gas fraction, baryonic mass, baryonic specific angular momentum plane. And you see that again, X-gas, Lastris, and Eagle really agree quite significantly well. So this tension with the simple idea of stability is also present in cosmological simulation. And look, it's not that surprising after all, because we know that the evolution of galaxies is not just a simple closed box scenario. But what is going on exactly? When we look at, when we have available cosmological simulation, we can also remove the selection effects from our observational sample. We can actually remove the gas fraction limit in X-gas and see what would happen if we look at the entire galaxy population, even the galaxies that are more gas poor than our detection limit. And this is what you find. So on the left, you have again the scatter around the plane if you use the X-gas detection limit. On the right, the big panel is if you get everything together. So you see that this massive tail of galaxies appears. And what does this mean? It means that even more gas-poor galaxies deviate from this plane. And actually, below the X-gas fraction limit, at least for Lastris and Eagle, this concept of plane completely breaks down. So that the gas fraction can go down, but the specific angular momentum of your system remains a decent specific angular momentum similar of a normal-ish disk galaxy. Again, reiterating that if we want to understand H1, as soon as we go below the very gas-rich regime, angular momentum is a very important quantity, but physics is much more complicated than that. And I think now trying to make the connection from H1 surveys with, let's say, large optical IFS surveys, if you think about this is not so surprising. It's just telling us that gas-poor galaxies or passive galaxies have a distribution of specific angular momentum that is not that different than galaxies in the star-forming main sequence. And if we use now a large IFU survey like the Manga Galaxy survey, now here the only difference is that I'm not measuring baryonic specific angular momentum because unfortunately I don't have the data yet. Here we go back to stellar spin parameter. And this plot might seem complicated, but what it shows, it just shows you per bin of stellar mass, what is the cumulative fraction of mass in the local universe, stellar mass, that is hosted by galaxies of different stellar spin. So you see, for example, that if you focus on the main sequence at 10 to the 10, you see the slow rotators, let's say the textbook ellipticals, contribute to almost zero, a very small percent of the global stellar mass budget in the local universe. Then most of the mass is on range of spins that are consistent with the spin of our Milky Way or typical disk galaxies. But the point here is the comparison between the two plots. The plot to the left are star-forming galaxies. The plot to the right are galaxies below the main sequence, or, to be specific, at least 0.5 dex below the locus of the main sequence. These are what large spectroscopic survey will call passive systems. And you see that above 10 to the 11, yes, there is a difference. Your number of slow rotators goes up. That's something that we've been known now for quite a while. But what I find remarkable is that below 10 to the 11, the difference between the two families is really, really small. There are tiny differences that are interesting, but they are small. And this also tells us that whatever is happening to the gas, whatever is happening to the star formation, doesn't really enters into any conversation about structural change in galaxies. And the process is that my quench and remove the gas have not necessarily able to change the structure of galaxies, at least in the local universe. So this is all I wanted to show you, just to flag that specific angular momentum and H1 are very interesting properties for galaxies. Of course, when we put everything together, things are always more complicated than that. And I think studies like that highlight that with the precursor and hopefully with SKA, there is also an important parameter space that we need to push towards, just push even below the X-gas limit in a resolved way for large statistical sample, to test this prediction and to test how much H1 and angular momentum are disconnected. Thank you very much for your attention.
Thanks very much, Luca. Any questions?
Hi, Luca. Christine Speckham at Queen's University in Canada. Great talk. I wondered if you had another piece of information, if it would allow to tease out the difference between angular momentum and H1 gas fraction. For example, if you had metallicity information.
Yes.
Do you think that would help further separate the galaxies that fall on where the prediction is strong versus not? And if not, what observable would you like to have to further illuminate
So
this?
that's a very interesting question. I think it goes back to what Romil was briefly mentioning yesterday about trying to dissect these planes and figure out which are the physical motivated parameters. But I think what we are trying to do now is that these are static snapshot of galaxies. The question is how galaxies move in this plane, because when we just look at the scatter, my personal view is that it's not that even in the main sequence galaxies move above and below. It's possible that the galaxy that is above now on the main sequence has been above the main sequence for quite a long time. And the same here when it comes to specific angular momentum. I don't necessarily think that galaxies above and below
are transitioning or have transitioned very recently. Probably we are seeing at objects that move in parallel directions. So the idea, again, metal lifting the local universe is great. Potentially pushing this to slightly higher redshift might be even more interesting.
Do we have any more questions? Pavel?
Thank you.
Hey, Pavel.
Yeah, it was a really nice talk. Do you think that there is some kind of contradiction between finding that at some point there is this association between the angular momentum and the gas content and perhaps morphology of galaxies with the well-known relation between stellar mass, angular momentum, and bulge to total mass fraction? Because, I mean, from this other relation, one would think that the morphology is always going to be linked to the angular momentum.
I would say that, I don't know if Mike is in the room, but I would say that the relation between mass, angular momentum, and bulge to total, it still needs to be dissected a little bit more, because what we are finding is that there might be a transition mass. I mean, above a certain mass, you have a lot of bulges. Below a certain mass, what I would call real bulges don't exist, but of course, when you do a bulge twist decomposition, you get a lot of bulges. So I think there is still a lot of work, because these are only 500 galaxies. When you dissect this, it's an interesting question, but I don't think we are necessarily in disagreement.
Thanks very much, Luca.
Thank you.
And we'll move now on to our next speaker, who is Carissa Button, and she'll be speaking to us about approaches to selecting strongly lensed gravitational H1 and OH sources.
Good afternoon. Thank you for the introduction. So today I'm going to share from my PhD work. I'm currently a postdoc at the University of Victoria, but I'm going to be sharing from my PhD, where I was looking at a statistical approach to search for lensed H1 and OH sources in the upcoming surveys with the SKA and Meerkat. So we've already heard quite a lot this conference about H1 and the science drivers and the importance of H1 in the baryon cycle. So I'm not going to spend any more time on this, except to mention that currently our high redshift measurements of H1 rely on indirect methods, and there's a need to complement and to cross-check these methods with direct detection of H1 at higher redshifts. So in addition to looking at H1, I was also looking at OH megamasers, and these arise from stimulated emission at 18 centimeters. Because the emission line is so close to the H1 emission line, these will be a major source of contamination in high redshift H1 surveys, but they're also very important science traces in their own right, because they trace extreme star formation as well as galaxy mergers. So that motivated us to look at both H1 and OH using the same methods. So in this work, we've been using gravitational lensing as a tool, and the magnification due to gravitational lensing can enable us to detect sources that would otherwise fall below the sensitivity of current instruments. Also, gravitational lensing has had historical importance in studying galaxy components at high redshift and has been used for all the major ISM lines across the electromagnetic spectrum. So this is a promising method for making a high redshift H1 detection. So the context of my work is the SKA precursor and pathfinder surveys, as well as looking forward to the SKA surveys themselves. And this table here at the bottom, you can see how many H1 detections we are expecting in these upcoming surveys. However, we are only expecting a very small number of these sources to actually be gravitationally lensed. And since confirming the lensed nature can be quite expensive, we need an efficient selection criteria in order to select the lens candidates out of the H1 surveys. So before I go into my results, I just want to show an example of how this work has been used before with the Herschel and the South Pole Telescope surveys to search for lenses. And the method makes use of the fact that the magnification bias increases the number counts at high luminosities. So here in the plot, you can see its flux density on the x-axis and integrated number counts as a function, per square degree as a function of flux density on the y-axis. And the solid red line shows the unlensed submillimeter galaxy population, while the dashed line shows the strongly lensed submillimeter population. And so at a flux density threshold of about 100 millijanskis, you can see that the dashed line lies above the solid line, and this is an efficient lens selection criteria. So this is what they used, and Negrello in his work found 80 lens candidates in the H-Atlas survey. Just to demonstrate this in a different way, if you take an image from your survey, it's the brightest sources in the image that are the ones that are most likely to be lensed. And you can then perform follow-up observations with a high resolution instrument. So we applied this method to H1 and OH. And the reason why we are interested in these lines is that in applying gravitational lensing is to search for these lines at higher redshifts, as well as to lower masses and to lower OH luminosities. Additionally, gravitational lensing could magnify source solid angles and enable spatially resolved H1 dynamics, as well as providing completely new traces for the dark matter foreground halos. I'm not going to go into any detail here, except that we have to calculate the lensing probability. This is based on the nature of the foreground lens, which we assume to be a dark matter halo. And here you can see the effect that the magnification bias has on the H1 mass function, where at higher masses, you can see that the lensed H1 mass function shown in the blue curve lies above the alfalfa H1 mass function shown in the green curve. So this can be integrated over to find the integrated number counts as a function of peak flux density. And this is what I'm showing here. This is a similar plot to what I showed for the Herschel survey, where we've got peak flux density on the x-axis and number counts per square degree on the sky on the y-axis. And the unlensed population is shown here in green, and the lensed population is shown in blue. You can see there's a point where the blue curve starts to lie above the green curve. This is where we can efficiently start selecting gravitationally lensed sources more than we are selecting non-gravitationally lensed sources. This figure is just for one redshift interval within the SKA bands, but I've calculated that point of intersection for all the different redshift intervals that are available to the SKA bands. And here it is shown for those different redshift intervals, also shown in the vertical lines, the approximate sensitivities of the SKA surveys. So here you can see that towards higher redshift, the source counts of the lensed objects starts to become more promising, but the flux density threshold at which we need to select these objects is still very deep. And so in order to build up a fair sample of gravitationally lensed sources in this way, we would need to survey the sky to quite deep, as well as quite wide. So in addition to looking at OH, we also looked at, H1, we also looked at the OH megamazes. And in order to do this, we first had to relook at the OH luminosity function, which has previously been fitted with a power law. I used a Bayesian approach to perform model selection between a power law and a Schechter function, and find that the Schechter function is marginally favored when all the data points from the original 2002 paper are used. But the form of the OH luminosity function needs to be tested as more OH megamazes are discovered in the future. So this work I've recently published, and this is just showing the number counts of the OH sources for different evolution scenarios. So in the OH case, we have to include the redshift evolution of the luminosity function, and we have parameterized it with this parameter beta. For higher parameter values of the evolution parameter, this method starts to become promising for selecting lensed OH sources, but at moderate or no evolution, this method is not really promising. I do want to point out that the flux densities here are much higher than in the H1 case and would be achievable with even the Mighty and Leduma surveys. So as an extension to the OH work, I've started looking at OH number counts in the MELS survey. And here I find that although we are not likely to detect lensed OH megamasers with this survey, it is a promising survey to start searching for new OH megamasers that could increase our sample of currently known OH megamasers. A further extension to this work has been to look at H1 at lower thresholds. As I said, in order to build up a large sample of gravitationally lensed H1, we would need both deep and wide surveys. A second approach would be to search at lower flux density thresholds, where we are not selecting predominantly lensed sources, but we're selecting both lensed sources and unlensed sources. And then to remove the unlensed sources using multi-wavelength ancillary data. So here I just show how the number density of the lensed sources would increase if we go to lower flux density thresholds. You can see that we are starting to achieve much better sky densities. Then we explored very briefly how we could start removing these contaminants using photometric redshifts that will be available in the future from a survey like LSST. And we used the SIMBA simulation just to see how this could work, and we find that the method will depend quite strongly on the accuracy of the cross-matching, but this method needs to be explored in a lot more detail. So in summary, I find that for H1 sources, we can find a flux density threshold at which we can start selecting lensed source counts more than we start selecting unlensed objects. And this flux density threshold will be available to the deep SKA spectral line surveys, but we'll also have to survey large areas of the sky in order to build up a reasonable sample. For OH megamasers, I find that the surface density of the lensed objects depends strongly on the evolution of the OH luminosity function. And in both cases, in order to try and improve the lensed surface density on the sky, we can try and use multi-wavelength information to remove high mass or high luminosity contaminants. So ongoing work is to start searching in the MELS data for OH megamasers, both lensed and unlensed, and also to explore different methods for distinguishing between massive galaxies from lensed galaxies using ancillary multi-wavelength data. Thank you very much.
Thanks very much, Carissa. Very interesting work. Do we have any questions from the audience?
Hi, Michael Bush. Thank you for giving half a talk on OH. Thank you. I was wondering, is RFI a big issue for OH megamasers at like moderate redshift? And does that kind of become less of a problem at higher redshifts when you redshift out of the RFI range? Thank you.
I haven't started performing these searches. In these number counts, I just exclude the RFI window for Meerkat, and then I just don't include any sources within that redshift range.
Okay. I have a question from online from Mark Verheyen, who is identifying as an LCR, so I'm guessing late career researcher. And he says, given that H1 morphologies can be complex and the lensing model uncertain, how large can the error in the magnification and thus the inferred H1 mass become?
I think it can become quite large. We have been using quite a rough model just based on previous work that has used this method to select lensed sources. We just applied the same range of maximum magnifications, but we haven't actually looked at specific systems and what their magnification is.
I think we have time for one more question, if there are any. Right, but if not, we'll move on and thank Carissa and move on to our final speaker for the session. And that is Bo Peng, who will be talking to us about galaxy dynamics revealed by a physically motivated model for the integrated H1 line profiles.
Hello, yes, can you hear me? Yes. So hello everyone, and it's a very lovely afternoon, and I am very honored to be here to present this work. And by the way, I'm a postdoc at MPA. Yeah. Yes. So in the past days, I have, and I believe you all have heard a lot of talks about how amazing these resolved H1 observations would be, and you probably would wonder why should we still care about the unresolved integrated H1 profiles. But it's important to bear in mind that the reality is, in the data archive of H1 spectra accumulated in the past many decades, most of them are integrated H1 profiles. And even in the future, these very important and probably very important surveys that are either ongoing or in the future, a substantial fraction of detection will still be unresolved or marginally resolved, especially if you care about the low mass galaxies or if you would like to observe farther away. Despite the still growing size of the data sample of integrated H1 spectra, the community still needs an automated, physically motivated, statistically robust, and parameterized way to characterize these spectra. And even if you just look at this integrated spectra, you can see many features that are in addition to the things we usually measure, like the width and the line center. You can see there's some symmetry, the edge can have different steepness, and there might be some little bumps at the side of the main spectra. There has been many previous attempts in trying to combat with this question because it's important but challenging. People have tried many things, including Gaussian peaks, Hermite functions if you combine the first and the second order of them. Sorry, there was a second order. Or the segmented functions or the famous busy functions. However, these models have their problems and challenges. The first challenge is that H1 profiles are very diverse and complex. You can see they can be double-horned, or they have a top flat, or they can only have one peak. They can also either be symmetric or symmetric. It's a non-trivial task to be able to reproduce these profiles in a single framework. And there are additional challenges, including how relevant physically these parameters are, or these models are, how reliable these models are, whether they have statistical issues, and so far these models can only be used on high signal-to-noise ratio, data. That's why I decided to try. Is there a way to be able to produce a model that can give you physical parameters, but also be able to fit these profiles? And this is the PanDisk model. And I will give you a very brief introduction of how I reached this point. It involves many assumptions and many compromises. The first assumption is that we only care about a single disk of the same rotational speed. This is very unique for H1 because H1 spectrum is integrated, intensity weighted. H1 surface density has this nice flat profile which eases the complexity of the need of convolution between the surface density and your rotation curve. And the better point of H1 disk is that it's very extended. So most of the H1 is coming from the flat part of the rotation curve. So what's dominating the integrated profile is this single speed rotating disk or ring. But there are more complexity, as you just saw, and this is my second assumption to cope with the symmetry. Because there's only limited information in the spectra, I made the simplest assumption that the disk or the ring has a constant angular surface density gradient. And this would be able to produce a symmetric profile like that. The third assumption is the velocity dispersion, or what makes the spectra look real. And I have to make another compromise to assume the whole disk has the same velocity dispersion, although it is certainly not true, as you have learned from many resolved studies. You should think this of as an intensity-weighted average of the velocity dispersion of the disk, or the V sigma at some characteristic radius. The fourth assumption is to deal with the trough. Usually you have different trough contrast, and this can be nicely attributed to the rising part of the rotation curve. This is an example. If you convolve the rising part of a rotation curve with a uniform surface density, you will end up with that dashed line, a single peak. However, this single Gaussian peak can have other origins. This is an incomplete list of them, and some of them are actually very broad. So with these parameters in hand, there should be some colors. Yes, I reached this model with 7 parameters. 5 of them control the line profiles, and 3 parameters are to deal with the disk, and 2 of them are to deal with the Gaussian component. The 2 additional parameters are rather trivial by shifting and making this profile higher or lower. But there is yet another task to be done, which is how to fit this profile. This is another very challenging thing, and the result that I reached is to use MCMT fitting. The most difficult part is that the fitting result may not be unique, and the final distribution of the parameter may be multimodal, and it can be solved by MCMC, although the drawback is that it's pretty heavy in computationally. And I would like to show you some of the fitting results. These are showing you how the model, which is shown by the dashed line, match with line profiles, no matter whether they have different prominences of the horn and whether they have different trough contrast, either there's one single peak or 2 of them. It also works very nicely on asymmetrical profiles. I further tested these profiles on several samples, including the high signal-to-noise ratio sample, signal-to-noise ratio controlled sample, and the spark sample to compare with the flat rotation curve. There are agreements and disagreements. The line width measurements are pretty good, although there are some limitations. For example, the VR, or the assumed inclination-corrected rotation velocity, or what I think of the deconvolved rotation speed, is actually not the rotation speed or the flat speed part of the speed. It turns out this VR is very sensitive to the structure in the rotation curve, and we know already in the past resolved studies that massive galaxies tend to peak in the rotation curve, but low mass galaxies have this rotation curve still growing, which overestimates and underestimates the V flat with VR. And W50 actually has a similar problem. The introduction to the model and the verification of the model is already published. If you search for PanDisk, you can easily find the paper. But with this model in hand, I was very excited to apply it on a much bigger sample of data, because The study of integrated line profile does not lie on precise measurement of these parameters, which you don't have so much information. It wins in the sample size. So it has been already applied on the full alpha sample with 31,000 spectra. It shows pretty good statistical agreement with, for example, W50 measurement, comparing the model-based and the alpha-alpha-based, which is, has manual involvement. Although there you can also see clear offsets, like on the narrow end, the model-based tends to overestimate the width. This is partly due to the flat priory in the MCMC fitting. And on the very wide end, you see the model is overestimating again. It's because some of the confusion made very broad features are picked up by the model. And I would like to show you some of the interesting results when you have so much data. The first is the broad wing. After applying it on the high signal to ratio, for example, I already realized some of them can have this very, very broad Gaussian component. You can see the Gaussian component shown by this dashed dot line as the decomposition. This has a relatively high occurrence rate, about 14% in the high signal to ratio sample. And it could be difficult to tell which is or what process is actually responsible for it. In terms of the distribution, this broad wing tends to be found in narrow profiles, and they tend to be edge-on galaxies. And when I check the optical images of these things, I think or speculate half of them are produced by confusion, but the rest are very difficult to understand, even if I have resolved data. Another interesting thing is the velocity dispersion. Looking at this spectra, I developed this impression that broader spectra would have gentle edge. I don't know whether you can see it from these different spectra or not, but it's relatively clear to me that you see this slopiness. And now I have the data to populate this figure. It turns out the profiles that are wider do have this velocity dispersion measurement, that the edge to be flatter. And it turns out this V over sigma thing, which high redshift people like to use to quantify the stability of the disk, is a mass-dependent value that ranges from 2 to 20 and tends to be high in high-mass galaxies. And if I play with the things around, I can understand the interesting scaling between the V sigma and the V rho in the previous figure by in the framework of two-marine stability. Basically, I can convert the V sigma over V rotational velocity square root to the critical two-marine surface density. And this is where the most data points lie, in this line, which is comparable to the H1 surface density that people usually see, which means in this framework, the H1 disks are usually marginally stable, and this sigma to velocity relation is likely regulated by the stability of the disk. And I cannot, and without mentioning BW Byronic Tally-Fisher, this is the most important application of H1 profile. If I use the inclination and profile-based sample selection, I can reach this amazing Byronic Tally-Fisher relation. It is composed of a very tight stripe of data with countable outliers. It looks too good to me. Consider that there are 3,300 data in this figure. And in addition to this, I can tell you why this is so tight. If I start from the full sample, it looks like that. With inclination cut, it only becomes somewhat better. But with profile-based sample selection, especially these three, which forces the profiles to be dominated by a double horn or disk component, they land in that region with a slope of roughly 3.5 and nicely together, with sample size between 4,000 and 700. If I apply all the profile-based selection criteria, I move further down in terms of scatter, but landing in the same solution with less sample size. So this opens up a possibility that there can be a very, very tight BTFI if you are able to select based on the profile. Yet another interesting thing is that the VR and W50 based BTFI, if I convert them to using the V flat, they would land up in the same, or predict the same slope for the V flat based BTFI of exactly 4, which is to be tested by the result studies. So I will leave my summary here, and I would like to take any question.
Thank you very much, Bo. I think one question before we all dash off to the tea break.
Thank you. Super interesting work. So I wanted to point out that the fact that the edges are more or less flat, that's actually a reflection of the rotation curve. If the rotation curve is flat, the edges are steep. Otherwise, that's just indication of rising rotation curves more than velocity dispersion. And also, just want to point out that Adam Watts did a PhD exactly looking into the asymmetry of single dish profile, looking into alpha X gas, SEM-H1, and simulation. So we can talk afterwards if there is time.
Yeah.
But super interesting, thanks.
Yeah.
Okay, there's one more desperate question here.
I apologize if I missed something. Can you please better explain to me, maybe at coffee, what is the physical motivation for the broad single component which we see there?
Oh, I just add a Gaussian, thinking that I need to account for the rising part of the rotation curve, which would look like something like this. But I didn't constrain the width of this thing and let it to be able to vary, and it's able to pick up many of those very broad things.
I think that there's lots more discussion to happen at tea, and so I'd like to thank all the speakers from the session, and I think we can close. Thank you.
I know that. So like, alles okay?
VR data, yes. There's talks. And there's a PowerPoint that's...
This one?
Yeah. Hope it works, because it has been made on a Mac.
It will work. Let me just copy to that computer as well.
Sure. Otherwise, I also have a PDF.
I'll open it now for you.
All right. Hi, folks. Get it? Ooh, tough crowd. I'm Eric Tollard from the Space Telescope Science Institute. I'll be your chair for this, the last session of this symposium here. Right? Fortunately, we have several talks that I expect will be excellent. And we'll be beginning with an invited talk by Pavel Manchera-Pina. Take it away, Pavel.
Yeah, thank you very much. Thank you very much to the organizers for inviting me to give this talk. I am Pavel Manchera-Pina. I am a fellow at Latin Observatory. And this talk is indeed about how can we test dark matter theories using observations of dark galaxies with the H1 line, from my very limited and biased point of view, of course. So, as you know, the collision-scale dark matter model is extremely successful at reproducing the large-scale structure of our universe, but when it comes to the low-mass regime, it sort of breaks down and it has lots of problems, as we can see here in this compilation by Laura Sales and collaborators. So because there are so many of these problems, it is just natural to wonder if alternative dark matter models can do a better job when confronted against the observations. So over the last few decades, different alternative dark matter models have been proposed. Many of them have already been rejected, but there are a few that remain, and those that remain are good because they can mimic the behavior at CDM at large scales, but they have lots of different predictions when it comes to the low mass regime. And this is not only about the very different halo occupation fractions, but also about the internal distribution of dark matter inside galaxies. And this for us is great because we can use dwarf galaxies to test these different models. And in particular, this is where the beauty of galactic dynamics and of the beauty of the H1 line comes into play, because it allows us to have resolved rotation curves up to very large distances, so we can trace very well the galactic potential. So the step 0 for this is to get the rotation curves, and it's very important to account for different observational effects like beam smearing. So when you do the kinematics of dark galaxies, you need to make sure you are using 3D kinematic modeling. There are many tools of this. I quote a few of them, but there are many more. But the important thing is to do it in 3D. So the 2D fitting doesn't work anymore, and I'm happy to discuss more this if someone in the audience wants to know more. Once we have the rotation curves, the circular speed profiles, we can then go on and use this famous method that has been there for 40 or 50 years at this point, which is rotation curve decomposition. And the idea is to assume that the circular speed is tracing the gravitational potential, and then to decompose the observed kinematics of the galaxies with the contribution coming from the baryonic components. In particular, for these dwarf galaxies, the gas is the one that dominates the baryonic component, and then the dark matter halo. And as I said, we have been doing this for 50 years, but in the light of all the upcoming surveys that will give a lot of data for H1, I think it was important to emphasize 3 things that are different when we do the mass models for dark galaxies compared to the more massive systems. And one of them is very obvious, and is the fact that we know dwarf galaxies can have dark matter cores, so therefore the functional form that you choose for your dark matter halo needs to be flexible enough to account for a dark matter core. The second thing is that while for massive spiral galaxies, the rotational velocity traces very well the circular speed, this is not necessarily the case for dwarf galaxies. So this means that the asymmetric recorrection is important, and we need to be then very careful when applying this positive correction to the rotation curve. In particular, we need to constrain very well the velocity dispersion of the gas. These 2 things are fairly well known. The third thing is not explored a lot, but it's something that I spent a lot of time with during my PhD thesis, and is the fact that we should leave behind the assumption of razor-thin disks. In particular, these gas-rich dwarf galaxies will have thick disks, and these disks are flared. And the gravitational potential for a disk that is thick and flaring is very different than from a razor-thin disk, and this can have important effects in the mass model. And I can show you some examples later if you are interested. And we have now ways to determine this, so if you are curious, please feel free to reach out. So I have done the task of going through all these different careful steps in a very nice sample of dark galaxies that are as good as you can get them at this point. And this means they have distances coming from the top of the red giant branch. They have near-infrared photometry. They have high-resolution H1 data from all these different surveys. And I have obtained 3D kinematic models, in this case with 3D Barolo. So we have robust rotation curves. And I will now show you the results of the mass models. And there are a bunch of things that I would like to show you regarding the baryon to halo connection for these galaxies. There are some quite interesting things, but I will focus mostly on the properties of the dark matter halos. And in particular, I will be looking a lot into this plot. So this shows on the vertical axis the circular speed of the dark matter halo measured at 2 kiloparsecs, so it's a proxy for the density of the halos, as a function of the peak velocity of those halos, which is a proxy for the mass. And to have a baseline, I show here now the result from cosmological simulations using cold dark matter. So this is where CDM predicts galaxies to lie. So now I will add the points from this mass model of these dwarf galaxies that I was just telling you a second before. And these are the results. So as you can see, the densities are typically lower than CDM, but this is not fully surprising because, as we know, we think most of these dwarf galaxies have dark matter cores, and those cores lower the densities. Now, what I want to emphasize, though, is that this sort of green envelope that you can see here, I will argue, is really essentially showing us the limits of how low you can go with CDM plus feedback. And the reason is because most of these dwarf galaxies have what I call maximum cores, and this is that the size of these cores is about 3 times the effective radius of these galaxies for many of them. And I think most simulations agree that you don't have enough energy available from supernovae to build cores larger than this. This is already on the generous side. So this is as low as you can get with CDM plus feedback. The problem is that there is actually no full consensus that stellar feedback can do this. And we hear all the time that baryonic physics can solve all the small scale issues of CDM, but I don't think we should take this for granted. In particular, we have very different simulations like TNG50, so big volume, cosmological, hydrodynamical, that doesn't manage to produce dark matter cores. And we also have very similar simulations like LIDA with super high resolution, and they don't manage to build cores either. So because of this, again, I think it's important to explore different options, and the other option is dark matter physics. So for the rest of this talk, I will focus in a couple of different dark matter theories that have been very popular over the last few years because they can build dark matter cores. And the first of them is fuzzy dark matter. So in the context of fuzzy dark matter core is a particle that is tiny. So it has this action has a mass of around 10 to the minus 20, 10 to the minus 23 electron volts. And what simulations found with this type of particle is that in the center you develop a so-called soliton or a core. And essentially this is very cool because it's a quantum effect. Essentially these are so small that the de Broglie wavelength is huge, of the order of kiloparsec scales. And so if something is below the de Broglie wavelength, it's going to behave like a very weird condensate, and essentially it creates these dark matter cores. There is a lot of very nice physics behind. You can solve the equations of Poisson-Schrödinger, and the ground state solution gives you this fuzzy dark matter. Don't ask me more, but I can show you some references. But the overall point is that you end up with this type of profile that has a core in the center, and then the outer parts, it mimics an NFW. So it turns out that this type of profile fits very well the kinematics of gas-rich dwarf galaxies, as you can see here in this plot that shows, this is work from Andrés Bañares Hernández at the IAC, and it shows 2 rotation curves for nearby galaxies, and you can see that these mass models, considering fuzzy dark matter, fit the data really well. So this will tell us that fuzzy dark matter is a very good candidate. However, it turns out that there are a couple of problems with this. So the first problem is that there is not one single value of the action mass that can match all the observations. So what this plot shows is the action mass that you get for the different dwarf irregulars in this paper that I was telling you before, and the difference larger than the uncertainty, so this is a problem. But this is even more dramatic because from the kinematics of ultra-faint dwarfs and from the abundance of Milky Way satellites, they put lower limits that are 2 orders of magnitude above what you need to fit the kinematics of gas-rich dwarf galaxies with fuzzy dark matter. So clearly this is a big problem. And the other big problem is that this type of action mass suppresses too much the small scale structure in the universe. An example of this, you have it here on your right. So it shows the stellar to halo mass relation that you expect for the best fitting action mass. And you can see that galaxies with stellar masses below 10 to the 8 in principle shouldn't exist. So this is clearly not anymore a good representation of reality. And I thought it was important to show because it's a very popular model, but these findings over the last couple of years show that, at least as we understand fuzzy dark matter right now, is no longer a viable option. The second type of model that is quite interesting is self-interacting dark matter. So the main difference between CDM and SIDM is that dark matter is no longer collisionless, particles can scatter, and this scatter is characterized by an effective parameter, which is the cross-section. What the different interactions do is that essentially they make all dark matter halos go through the so-called gravothermal evolution that is depicted in this plot here. So essentially this shows the evolution that any dark matter halo in a SIDM universe should have. And as you can see, at first it will go to an expansion phase where you lower your densities. So here you create dark matter cores. And then at some critical point, they will start to collapse again. So the thermalization is too efficient. At some point, it's too cold, so the halo collapses again. And when this happens, essentially depends on the cross-section of the dark matter particle and the initial conditions of the halo. And the main result of this is that at redshift 0, we are going to expect to see galaxies, both massive and dwarfs, that can have very large dark matter cores, and also that can be cospier than an NNW. So because of this, SIDM is a great candidate to solve things like diversity of rotation cruise problem. So we wanted to check now if this SIDM can work for this set of dwarf galaxies. And the answer is yes. Just as a reminder, this is what happens with CDM plus feedback. And as I hope you can see, SIDM halos produce many of these blue halos. Again, this is a cosmological simulation, only dark matter for SIDM. And many of these halos are perfectly consistent with the same thing that stellar feedback can do. So SIDM produces these squared halos. And now we have the same problem that we're back at square zero, right? Because which one is the right one? Is it CDM plus feedback, or is it the physics of dark matter? So it's essential to keep getting data. I think we will have very important information from oncoming surveys. But I will try to make the point that we may have a galaxy population that might already be able to help us disentangle between these two. And this galaxy population is that of ultra-diffuse galaxies, or UDGs. We will hear more in a second about this. Once I shut up, we will have a very great talk on UDG, so I will just give very few details. And what characterizes ultra-diffuse galaxies, in principle, is the fact that at fixed stellar mass, they have a very large effective radii, so they have very low stellar mass surface densities. Now, they are fairly unexplored dynamical population, and it's important to correct this, because besides the large size, UDGs look pretty much like other dwarf galaxies, but it's the kinematics what really sets them apart. And over the last few years, we have been looking, together with my collaborators, at a number of gas-rich ultra-diffuse galaxies in the field. So they are full of gas. Turns out they have nicely rotating H1 disks, and they show a number of very puzzling kinematic properties. One of them is that they are strong outliers of the magnetic-Tulip-Fisher relation. And I want to emphasize that these galaxies, they don't have messy kinematics. They have regular velocity fields. There is a wide range in inclination parameters. Some of them have high inclination. So these are not just phase-on galaxies for which we miss the inclination correction. I'm happy to give you more details if you want. But I think this will become very clear when we look at those galaxies for which we have the best available data. And there are these three galaxies here. You can see on the top the optical imaging, and on the bottom is VLA imaging, and now fantastic Meerkat data that are just beautiful. And you can see in these three examples a galaxy with inclination of 30 degrees, 70 degrees, and 50 degrees. So those are not edge-on galaxies, I hope, phase-on galaxies. I hope we are going to agree. So for these systems, I have derived now the mass models of the galaxies, and the mass models look something like this. So what you see there is the contribution from the baryons, from the gravitational potential of the baryons in blue. The best fitting dark matter halo is in black. The total mass model is in red. So we can get very good mass models, but the price that we have to pay for this nice agreement, thank you, the price that we have to pay for this nice agreement is the very low concentration parameters. And these concentration parameters are something like 5 to 8 sigma below the expectations of CDM. And this disagreement becomes very clear when I go back to this plot of B2KPC versus Bmax. As you can see, these halos are beyond what CDM plus feedback can do. So if there is not enough energy to build cores larger than this, I think this really shows that in CDM, these galaxies are a problem. So I wanted to look then in the case of SIDM. And here the picture changes dramatically. This is the same plot that I was showing you before. But as you can see, there are many of these halos in these simulations that manage to produce halos, many halos in those simulations that have densities as low as those that we observe in these ultra-diffuse galaxies. So I think this shows that, that they are a natural outcome in SIDM. And actually, with this, I come to my conclusions. I would love to have time to discuss with you. What I have, these are my main take points, and is that the kinematics of classic dwarf irregular galaxies can be fitted with both CDM if feedback works, and SIDM. Fuzzy dark matter looks like it's no longer an option, but SIDM remains like a strong candidate based on the kinematics of dwarf irregulars and of ultra-diffuse galaxies. So of course, gas-rich are key to keep testing these alternative dark matter models, and I think we may have with us already a population that can help us to disentangle between baryonic physics and dark matter physics. So in fact, if you are in the Meerkat committee or if you have friends there and you see a nice proposal to obtain a large sample of ultra-diffuse galaxies, please see it as a no-brainer because we can really set constraints on the nature of dark matter itself with this type of galaxies. Thank you very much.
All right, we have plenty of time for questions. A couple there.
Hi, Paolo. Thank you very much for the amazing talk. Can we go one slide back? Another one for dark matter. No, back, but to highlight the dark matter part. Can you please explain to me what are those two green points at very low velocities, how their Vmax can be even compared to Vmax from dark matter models, because there is not only core cast problem, there is also too big to fail problem. These Vmaxes cannot be comparable. So why they're matching so well, and why the rotation curves at all would trace the gravitational potential in that regime?
Yeah, these are two, thanks for the question. These are two very funny galaxies. First of all, as you have noticed, these plots are still in preparation. That doesn't have uncertainties. But just for you to have a number in mind, should be around 5 kilometers per second or so. So those two galaxies are in the sample of little things. If I recall correctly, this is DDO 126 and CBN something. So these are two galaxies that have very low rotational velocities. And essentially, they have very thick gas disks. And because the gas disks are very thick, the contribution to the circular speed is very low, and so the gravitational potential is really dominated by the dark matter. So that's why they really trace very well each other, I think. And I think this also shows that it's important to take into account the thickness. And you see it in the two galaxies with the lowest rotation velocities, for which the velocity dispersion is the largest, so they are among the thickest disks.
Any questions on Zoom or online? Okay, cool. There's one over here then.
Yeah, hi Filippo Macagni from ENAF. Thank you, Pavel, for the nice talk. I was wondering if you can add something about the information that we know about the environment of these UDGs, and of course Meerkat will be important also for that. And because also we saw in the other days that now environmental effects also occur in filaments and in a less denser environment, and if you think that this could be something important for their evolution and their being off-little efficient. Thanks.
Yeah, thank you for the question. So these galaxies, I should have said it, emphasized it, they are selected to be isolated. And by isolation, I mean that there is no confirmed neighbor within 1 megaparsec, one projected megaparsec, and plus minus 500 kilometers per second. So I think it's a fairly good constraint on the isolation. What I can tell you in terms of the Barrington-Fisher relation, for example, is that because today we see them in equilibrium as regular rotating disks and without the massive galaxies around, I think you can interpret them right away. You don't need to take into account different effects. And I'm thinking here of alternative dark matter theories, such as like MOND, for example, right? That if you have a massive neighbor, you will expect these sort of deviations, but this is not the case for these galaxies.
Any questions?
From Mark Verheyen, in rotation curve decompositions, Vmax is degenerate with the core radius. Could you systematically overestimate Vmax?
So if I could systematically underestimate the size of the core, I guess is another way to think of that, right? So for these galaxies, I think it's quite interesting because in fact, what you could do is to have a much larger dark matter core. I think I may even have a figure where you can have a halo that has a normal concentration, but it has a huge core. The problem with this is that the typical size of these cores, I have it here, these are two examples for these two galaxies. So in this case, the dark matter halos have normal concentrations. The problem is that the dark matter cores are 20 kiloparsecs and 15 kiloparsecs. And if you look at the velocity, these are tiny bars, right? So the typical virial radius for these systems is going to be like 40 and 60 kiloparsecs. So essentially the cores will need to be 1/3 of the virial radius. And as I was saying, there is just not enough energy available in supernovae to build cores of this size. So I think that's why UDGs are cool, because they can help you break this degeneracy that Mark is pointing out, because you cannot have cores that have this size with supernovae.
Probably time for a 30-second question. Okay, go ahead.
Yeah. Sushma from UCT, and I wanted to ask whether you actually did the correlation between the core radius and stellar mass, or like baryonic surface density, because you have different predictions from baryonic lambda CDM predictions and SIDM predictions, where you see maximum, core sizes for intermediate galaxies if it is baryonic lambda CDM, and for low baryon surface densities you would see more cores if it is SIDM, right?
So I haven't looked in detail into correlations with the dark matter core, but it's a bit of a circular argument, because when you do the mass model, you assume that the core radius is somehow proportional to the effective radius, so there will be a built-in correlation there. So I'm assuming that if you have galaxies at fixed mass, those that have larger sizes will have lower star formation, lower stellar mass surface densities. So I think that gives you a correlation right away, but I haven't looked in detail into this. What I can tell you is that that for these surface densities, I'm repeating myself a bit, but the energy that is available there is not enough to build the cores as large as you need. But I can show you in more detail the typical size of the cores.
Thanks.
All right. Let's thank our speaker one more time.
Thank you.
There you go. Next up, we have Kadia Motiwala. Let's get that talk up there. There we go.
All right. Hi, everyone. Thank you so much for allowing me to speak to you today. I'm going to be presenting the work that I've been doing as part of my master's thesis, which asks the question, are gas-rich ultra-diffuse galaxies and field dwarfs two distinct populations? And we've already heard a bit about UDGs at this conference so far, but I thought I'd recap in the context of my work. So, while similar objects have been found in the past, UDGs were first found in large numbers in the Coma cluster by Van Dokkum et al. In 2015. And in this figure by them, you can see that their Coma cluster objects, shown by the red points, have physical sizes larger than 1.5 kiloparsecs and central surface brightnesses fainter than 24 mags per arcsecond square, making them larger than your typical dwarf galaxies and fainter than the Milky Way by about a factor of 100. And this definition that Van Dokkum et al. Proposed on the basis of size and surface brightness has since been widely used in the field as a criteria for a galaxy to be classified as a UDG. So this is an image of the largest UDG in their Coma cluster sample. And as you can see, it's quite red, which indicates that it's quenched and not actively forming stars. And we find that this is typical of cluster UDGs in general. As well as in clusters, we also observe UDGs in lower density environments, such as in the field, where they tend to be bluer and therefore actively star forming, and so we predict that they're gas rich. And their gas richness can be a very useful probe into the properties of the galaxy, but most crucially for us, it can provide a measure of distance, which, as you know, for such faint and isolated objects, it's a very difficult thing to measure. So we exploit the H1 reservoirs of these gas-rich galaxies to compile a catalog of known UDGs with confirmed distances. And I'll talk more about this catalog later on. But this observed diversity in UDG properties begs the question, how do these objects form? And if we go back to the plot on the right, we might start to guess as to the different formation pathways that might be possible. So, for example, we might start out with a Milky Way-sized halo that fails to form stars due to gas being removed from the galaxy from tidal stripping or ram pressure stripping. That would push the galaxy to lower surface brightnesses and into the UDG regime in the direction of this arrow. Or perhaps we start out with a dwarf-sized galaxy that's quite compact, but then puffs up due to some mechanism like feedback from intense periods of bursty star formation, which would expand the dark matter halo and redistribute stars to larger and larger radii, making it extremely buffy and ultra-diffuse in the direction of the orange arrow. And this is a scenario that's predicted by the Nihau simulations. Or maybe the UDG progenitor has undergone a major merger that would increase its angular momentum and cause star formation to be migrated to the outskirts of the galaxy, and therefore also buffing it up. And this scenario is predicted by the Romulus 25 simulations. And we can sort of test these formation models by comparing the simulated galaxies to observations, But the key question in my research is, are UDGs just the extended low surface brightness extreme of the dwarf galaxy population, or is there something really unique about them? And we address this question using two tools. So the first is observations. And historically, large samples of confirmed UDGs have been missing because, as I said, distances are difficult to measure, but they're also crucial to classify UDGs. But to our advantage, field UDGs, we can follow them up in their H1 and obtain their distances spectroscopically. And so we use the smudges survey for that. And I'll come back to smudges in a minute. We also make use of the Romulus 25 and Nihao cosmological simulations to shed some light on how these UDGs form and whether that physics is different to the physics that forms regular dwarf galaxies in these simulations. And so in this work, we compare gas-rich UDGs in both simulations and observations to dwarfs to see if there's any significant differences between the two. So starting with our observations, some of you might be familiar with the smudges survey. And this is a catalog of over 7,000 UDG candidates that are selected from optical images from the DESI Legacy Imaging Survey. And of these 7,000 UDG candidates, 378 are selected to be followed up in their H1 based on several factors like their magnitude and whether they have archival UV data. And then they're followed up with the Green Bank telescope, which, as you know, is a 100-meter single-dish radio telescope. And so we end up with 110 H1 detections, of which 37 can be classified as UDGs based on the Van Dokkum et al. Definition, and the rest as dwarfs. And along with optical photometry from DESI and H1 spectra from the GBT, every galaxy in our sample also has archival GALEX UV data that we can use to calculate star formation rates. And so smudges is a really nice multi-wavelength sample that selects UDGs and dwarfs using the same selection criteria, which makes it really well suited to a comparison study of the two populations like this one. So here I present the full extent of our comparison observation and simulated samples. For our simulations for Romulus, we make use of the sample presented by Wright et al. And for Nihao, we make use of the sample presented by Blank et al. But to both these parent samples, we make several cuts to only select the gas-rich star-forming galaxies that match the properties of our smudges observations. And I'm happy to talk more about these cuts later on. So in this plot, we have central surface brightness against effective radius. And I've put both simulations and observations on this plot. So the squares are the Romulus simulated galaxies, triangles are Nihao simulated galaxies, and the circles are the smudges observations. And this dashed line at 24 max per arc second square is the definition of a UDG in this space. So everything below the line is a UDG, and everything above is a dwarf. And there are two key takeaways from this plot, I think. So the first is that UDGs and dwarfs form a continuum in the space in both simulations and observations. And we don't really see any evidence for any distinction or bimodality here. And the second thing is that simulations and observations lie on top of each other and they're consistent, which sets us up for any comparisons that we make next. So here we have star formation rate against stellar mass, or the star-forming main sequence. And as you can see, the smudges observations, which are shown by the circles, follow the same relation as the simulated galaxies shown by the squares and triangles. However, quite clearly, you can see there's a difference in scatter, where the simulations have a much higher scatter in star formation rate than the observations. And this could be due to several reasons, but we think that the most likely reason is the way that star formation is prescribed in simulations, where it tends to be more intense and bursty. Another thing we see here is that UDGs in both Romulus and Nihao have consistent properties. And this is interesting because, as I said earlier, they form them in different ways. And I'll touch on this a little more later. So the Nihao simulations actually make the prediction that for a given stellar mass, larger galaxies should be more gas-rich. And so we test that prediction by I've plotted here the ratio of the H1 mass to stellar mass, or in other words, gas richness, against effective radius. And so we can take a more detailed look at this plot if we divide all the points into stellar mass spins. So this is the same plot as the last slide, but now the colors represent low, intermediate, and high mass spins. The stars represent the median in each spin, and the error bars are the interquartile ranges. So there are a few things going on here, but the first is that the low mass galaxies lie systematically higher in gas richness than the intermediate and high mass galaxies. And this makes sense intuitively, right? Because gas forms stars, and the more stars there are, the more gas has been depleted. And secondly, what we see is that for a given stellar mass, we see this hint of a positive correlation in gas richness and size, which again is something that NIHA predicts. We can further divide this plot into observations and simulations. So the center plot is the medians of just observations, and on the right, just simulations. The dashed lines connect medians of UDGs, and the dotted lines connect medians of dwarfs. And in both observations and simulations, we see that hint of a positive correlation in gas richness and size for a given stellar mass. The NIHA simulations actually further predict that UDGs should be, in general, more gas-rich than dwarfs. And we don't see that here in either observations nor simulations. However, when we look at simulations, we can see a hint visually only, we can see a hint that the UDGs lie systematically higher than dwarfs. But again, statistically speaking, the gas richness of UDGs and dwarfs are consistent in observations and simulations. So coming back to our original question, are gas-rich UDGs and dwarfs distinct in any way? And I think our study has shown that in all the observables that we look at, we don't see any difference in the properties of UDGs and dwarfs, including gas richness, which was predicted to be different by the simulations. And so the simplest explanation seems to be that they aren't distinct populations. A supplementary question could be, are UDGs in observations and simulations different? And again, we see that generally the simulations and observations show consistent properties, except in star formation rate, where we saw that high scatter in the simulations star formation rates, which we think is due to the star formation prescriptions in simulations. And lastly, we don't find any difference in the properties of the UDGs formed in NIHA versus those formed in Romulus 25, which again is interesting because they form them in different ways. But that's not to say that both bursty star formation and major mergers can't be happening concurrently in both simulations, but rather that the resolution and volume limits of each simulation only allow us to isolate one effect in each simulation. So both bursty star formation and major mergers could be happening or could be at play in the universe, or perhaps even both could be happening together. But taken together, I think all of this suggests that UDGs and dwarfs in the field are not distinct populations given their present universe properties. Thank you.
Any questions? Actually, any questions online first? Not yet. All right. What about in the room? Any questions? All right. Well, I have one. So in the last talk, we saw kinematics matter a lot, right? Did you do any comparison of kinematics between the observations and simulations?
No, because we only have like unresolved spectra for now. However, we just obtained four observations with the VLA for 4 bright UDGs from the smudges sample. So that's something we're looking forward to, doing kinematics with those. Yeah.
Cool. Any questions that have shown up? There's some here.
Hi, very nice work. I was curious in your surface brightness size plot, back when you select here, there is clearly a diagonal trend, which is most likely a selection effect.
Yeah.
Because, I mean, it's inevitable when you go to lower surface brightness, your size goes down. I was wondering, have you thought of if and how this might cascade down in your trends when you split galaxies as a function of mass and look at the relation between gas fraction and effective radius?
That's a good point. And I think we have tried to be, I guess, conscious of all of the different effects that might trickle down. I'm not sure if I can answer that immediately. Okay.
You could do it in 30 seconds.
Yeah, thank you for the great talk. Are you I mean, the in-house simulations, they make the UDGs, as you were saying, to the burst star formation histories,
Yeah.
and they put so much feedback that they break things like the stellar specific angular momentum mass relation. So clearly they need this feedback. So aren't you surprised from the fact that you find a lower scatter in your data in terms of star formation rate mass relation, as you were showing, but yet you managed to reproduce the trends in in-house? Is it
I think,
expected?
yeah, I think we were kind of surprised by how consistent everything was. But I guess, sorry, do you mean like how things were consistent between the simulations or between the simulations and observations?
Between observations and simulations, I was thinking, if you don't have all that scatter, maybe you shouldn't be able to reproduce the other parameters.
Right. Huh, that's interesting. I'll have to think about that a little more. Thank you.
Let's thank Khadija one more time. And, let's see. There you are. Archishman, yeah, go on up there. Yeah. So our next speaker is Archishman Kasnovas, to move us on from the topic of UDGs to something. Yes,
Sorry.
green peas, but what's going on here?
Yeah.
There we go.
Great.
Go ahead.
So, hello everyone. I'm Archishman Kasnovis, and I'm a PhD student at the National Center for Radio Astrophysics in Pune, India. I'm working with Professor Nisim Kanikar, and I'll be talking about the H1 properties of a very unique kind of dwarf galaxies in the local universe, which are called green pea galaxies. So before going into green peas, let's briefly talk about the epoch of reionization and the galaxies which are believed to have driven cosmic reionization. So very briefly, reionization is a phase transition of the universe, when the universe transformed from a homogeneous neutral state to a predominantly ionized and clumpy state. And it is believed that dwarf star-forming galaxies at redshifts greater than 6 drove the process of reionization. And the idea is that leakage of ionizing radiation or Lyman continuum photons, photons having energies greater than 13.6 electron volts, leaked from these high redshift star-forming galaxies, and those photons ionized the H1, the neutral hydrogen present in the intergalactic medium. And that's how reionization progressed. So a lot of these EOR galaxies have been detected in Lyman alpha emission, and that is why such galaxies are also called Lyman alpha emitters. However, the escape of Lyman alpha and Lyman continuum photons from these galaxies depend on the local conditions. Now, unfortunately, we don't really very well understand this dependence of Lyman alpha and Lyman continuum photons on the local conditions of these high-redshift galaxies, especially because these galaxies are very faint. So a possible solution to this problem is to find similar galaxies in the local or low redshift universe. Green pea galaxies exactly fit in this category. So green pea galaxies are some of the very good or some of the best local analogs of your galaxies, and quite a few of them have very high Lyman alpha and Lyman continuum escape fractions. And thus, green peas offer a very good approach to understand the local conditions of the ISM of the high redshift star-forming galaxies, which are supposed to have driven reionization. So, well, what are green peas and why are they interesting? Well, green peas are dwarf starbursts. They are found in the local universe below redshifts of 0.3, and they're characterized by very strong O3 5007 angstrom line emission in their spectrum. So a lot of these, the green peas have a lot of these green peas have very strong Lyman alpha emission, and they have similar Lyman alpha equivalent with distribution as redshift greater than 2.8 Lyman alpha emitters. More interestingly, green peas have low dust content, they have very little metallicity, and they also exhibit compact or interacting morphology, which are very similar to the high redshift LAEs, Lyman alpha emitters. But perhaps the most interesting aspect of the green pea galaxies is that many of them, or quite a few of them, show Lyman continuum leakage. And the leakage fraction kind of ranges from about 2.5% all the way up to 72%. And this is very interesting because this is kind of what we expect your galaxies to have. They should have significant Lyman continuum leakage. And this is actually quite rare for the galaxies in the low redshift universe. I mean, galaxies having Lyman continuum leakage. Other than this, green peas have high O3 by O2 ratios. And Jasker and Oe in 2013 argued that such high O3 to ratio basically implies that the green peas have a lot of ionized gas in them. So the presence of a high ionization state like the O3 would imply that the galaxy has a very strong ionizing radiation field, which would basically ionize a significant fraction of the gas in the galaxy, which would in turn facilitate the escape of Lyman continuum photons. So this is what Jaskanoid argued, and later on it was found that many galaxies, including green pea galaxies, with Lyman continuum leakage indeed have high O3 to ratios, and by high I mean typically above 10 or so. So green pea galaxies, from all these results, we see that green pea galaxies are some of the best local analogs. They're some of the best local laboratories that we have for understanding the physics of the high redshift EOR galaxies. Well, why should we study H1 in green peas, atomic hydrogen in green peas? Well, primarily because H1 is the main fuel for star formation. And also, the reason for the intense star formation activity in these green pea galaxies is not very well understood. There is another problem, and that is H1 resonantly scatters Lyman alpha photons and also absorbs the Lyman continuum photons. So because these galaxies show, a significant fraction of these galaxies show Lyman alpha and Lyman continuum leakage, this suggests that they should have low H1 column density so that these photons can come out of these galaxies. But at the same time, the starburst activity, the high star formation activity in these galaxies demand the presence of high column density H1 gas. So for these reasons, we need to carry out detailed 21 centimeter studies of green pea galaxies, and also more preferably mapping H1 in these galaxies. So the first detections of 21 centimeter emission from green pea galaxies were reported very recently by Kanekar et al. 2021 in a sample of 40 green peas at redshifts of about 0.02 to all the way up to 0.1. And this survey was done using the Green Bank telescope and the Arecibo telescope. There were about 19 detections of H1 21 centimeter emission and 21 upper limits on the H1 mass. We wanted to extend the survey. We wanted to have a bigger sample, and so that's why a new GPT survey was carried out on a sample of 24 green pea galaxies at redshift 0.045, and this led to 7 new detections and 17 upper limits, 3 sigma upper limits on the H1 mass. Finally, now basically we have a fairly large sample of about 62 green pea galaxies with 21 centimeter observations. And out of these 62 green peas, we have 25 detections of H1 mass and 19 upper limits for green peas with O3 to ratios less than 10. However, we have only 1 detection and 17 upper limits on H1 mass for green peas having O3 to ratios greater than 10. So these are some of the spectra from the current GBT sample. As you can see that, well, in some of the cases, like in this one, the peak of the 21 centimeter emission is not really at the expected line frequency. So the vertical dashed line kind of represents the frequency at which the H1 line should be observed. Here we can see that the H1 line is slightly offset from the expected line. A possible reason could be because the GPT beam in the L band is about 9 arc minutes wide. So that's a very large beam. And so we could have companion galaxies in the beam at redshift similar to the green pea. And what might be happening here is that we are actually picking up H1 emission from the companion galaxy instead of the green pea itself. And here also we can see that there are 2 components which could be from a companion. Here actually we have identified a companion from the optical images. By the way, I should mention that all of these green peas that we are observing in H1 are actually taken from the Jiang et al. 2019 sample, which is the largest sample of green peas till date, which has about 1,000 green pea galaxies between redshifts of 0.01 all the way up to 0.4. So we basically target the green peas at the lower redshift range because we want to detect the H1 emission from them. And here also you can see that the peak is slightly offset from the expected frequency. Maybe it is also because of companion. So moving ahead, let's talk about some of the results that we have gotten. So I'll just show some of the very interesting results that we have found in the interest of time. So here we have actually tried to see if the H1 mass of the green pea galaxies depend on the O3-2 ratios. So what we have done here is that here is the full sample, and we have divided the full sample into two groups, and this is divided based on their O3-2 ratio. So the left one here is for the green peas having O3-2 ratios less than 10, and this is for the green peas with O3-2 ratios greater than 10. And as you can see, that we asked the question whether the H1 masses of these two groups of green pea galaxies are drawn from the same parent distribution. Because we have a large number of non-detections in our sample, we use survival analysis for this purpose, and using a two-sample test, which also, in this case it's the Peter-Prentice test, we find that we can reject this null hypothesis that these two groups of green pea galaxies are drawn from the same distribution at about 99.9% confidence, which, assuming a Gaussian distribution, is greater than 3 sigma. So we have statistically significant evidence that green pea galaxies with O3-2 ratios less than 10 have H1 masses different from green peas with O3-2 greater than 10. And also you can see that the detection fraction for the green peas with higher O3-2 ratios is quite less. Here there is just only 1 detection out of 18 galaxies, and here we have about 25 detections out of 44 galaxies. So here the detection rate is much higher. Also, here you can see that these points are basically the mean H1 masses for the green peas in the two groups, and these means are also done using survival analysis. And as you can see, that the mean for the green peas with O3-2 greater than 10 is about an order of magnitude lower than the ones with lower O3-2 values. And this is actually consistent with the fact that these are the green peas which we expect to show Lyman continuum leakage. Because if there is not a lot of H1 gas in these galaxies, that is actually beneficial for the Lyman continuum photons to escape the galaxy. So we try to do a similar exercise for the H1 gas fraction. So this is H1 mass divided by the stellar mass as a function of the O3-2 ratios. And here we don't really find a very strong evidence of these two groups being drawn from different populations. The null hypothesis can be rejected at about 98.9%, which is definitely slightly less than 3 sigma. But we do have some evidence, at least at the greater than 2 sigma level, that these two populations of green peas are, the gas fractions of these two populations of green peas are drawn from different distributions. So this is perhaps, I think, one of the most interesting results that we are seeing. This is also the final slide. So here you can see that the left panel shows the H1 mass of the green pea galaxies versus their absolute p-band magnitudes. This black solid line is the MH1-MB relation for star-forming galaxies in the local universe, and the dashed lines are basically plus minus 2 sigma uncertainty to this to the local MH1-MB. And this is for the green peas with O3-2 ratios less than 10, and this is for the green peas with O3-2 ratios greater than 10. Here you can see that many of the green peas are actually above the local MH1-MB, and about 11 out of the 25 detections are above the plus 2 sigma of the MH1-MB. It could be the case that the O3-2 greater than O3-2 less than 10 GPs are gas-rich GPs, or it could be also the case that there are companions in the telescope beam. But more interestingly, if you look at the right panel, this is for the green peas with O3-2 ratios greater than 10. And here you can see that majority of these, so although there is just one detection in this case, the majority of these green peas have upper limits below the MH1-MB relation. So it could be the case that these are indeed gas-poor galaxies. And this is again consistent with the fact that these are the ones which we expect to be the Lyman continuum leakers. So we basically find evidence of a possible bimodality in the H1 content of the green pea galaxies. So like the lower O3-2 ratio green peas, many of them are gas-rich objects, and majority of the O3-2 ratio greater than 10 GPs are gas-poor objects. So yeah, and one possible reason, so what we think is going on here is that is that the O3 less than 10 GPs are basically ongoing major mergers, and we have evidence for this for quite a few GreenPs from GMRT and VLH1 mapping data. 2 of them have been published. And so the H1 is in the process of being consumed by the high star formation activity. Whereas this, for the O3 to greater than 10, they are actually tracing, they could be, I mean, this is just a hypothesis, that they could be tracing GPs at a much later stage of the merger, where the H1 has been depleted in the starburst. And that is why they are gas poor, and that facilitates the escape of Lyman alpha and Lyman continuum photons. So yeah, with that, I'll leave you with a summary, and thank you for your attention.
All right, unfortunately, that leaves us no time for questions, but our next speaker is online, so maybe there's just a moment while we get that brought up. Had anything really burning? 15 seconds or less in the back there.
So, nice talk. I have very little time, so we can talk more later. But have you considered the geometry of the gas, that there might be holes in somewhat more
Yeah, right. So that's why we are trying to do H1 mapping studies for these objects, so for the detections, I mean. And for 2 of the published works, we have seen that the GreenPs are actually merging with other objects, and we see very disturbed H1 distribution. So this is something which we have seen for a few objects. And although I haven't shown those results here, but we are carrying out deep mapping studies for the GreenPs to see if there are holes or regions of low H1 column density in the H1 distribution of these galaxies. So, yeah.
Thanks. Let's thank our speaker one more time. And we should have Zoom up there, since this is a remote speaker. Are we having trouble with the Zoom? Oh. Yeah, it should be Ayessa. Then they haven't started sharing their screen, or they're not there?
Hi there.
There we go.
Sorry.
All right.
Okay. Can you hear me well?
Yeah, we hear you fine. Let's just get the, looks good now. All right, go ahead, Ayessa Guimarães Silva, to tell us about Global Void.
Thank you. Hello, everyone. My name is Raissa. I am a first-year PhD student from Brazil, and I'm going to talk about dwarf galaxies in the local void using Wallaby data. So to kick this off, I want to mention what I mean by void. So void are regions that have a galaxy density that is less than 20% of the cosmic average. And they basically are most of the space that we see. So here I'm showing the distribution of galaxies, and we can see that between them, there are these empty or underdense regions, which are the voids. And we know throughout the symposium, we have seen that lots of people have been working with different environments, and we have these connection between different properties of galaxies and their environments. Here I'm showing only one, the star forming fraction, depending on the environment. So we can see that on denser environments, we have less star forming galaxies. And in voids, we have over 50% of galaxies are star forming. So galaxies in voids, they are younger, bluer, and star forming, and they're usually dwarfs. And I think that one of the most interesting facts is that about void galaxies is that cold dark matter predicts that they evolve more slowly than filled galaxies. And due to the hierarchical forming of galaxies, we can use these galaxies to investigate galaxy evolution in environments that are isolated from effects of more massive galaxies. So their evolution is more, I don't know, easy to pin. And what I mean by dwarf galaxy here are galaxies that are similar to the Large Magellanic Cloud or have lower mass. And we can see here in this plot that the effect of the environment on these galaxies is even more pronounced than on massive galaxies. So on voids, the fraction of star-forming galaxies, low-mass galaxies, is basically 1. And one of the most interesting questions that we can use these void galaxies to answer and to investigate is the growth and evolution of galaxies. So we can do this by studying, in this case, using H1 specifically, studying the accretion of gas from the intergalactic medium. So this is important for the gas supply of star formation. And one of the open questions we can say is how important is this accretion of gas? So there are basically 2 answers. And for this, I'm going to show the example of KK246, which is a galaxy in the Thule void. This galaxy shows evidence of gas accretion. So there is a very extended H1 disk. It has kinematic signatures of accreting gas. However, when we look at the same galaxy through the lens of metallicity, so in this case here, I'm showing the mass-metallicity relation, it shows to be a normal galaxy. Like, it doesn't show the expected behavior of a galaxy that is accreting gas, so it should be lower on the mass-metallicity relation. So this is something that is common in void galaxies, in low-mass galaxies and voids. And this is what motivated my PhD, basically. So in my PhD, I'm aiming to investigate these objects through both their gas content and their metal abundances and star formation rates, and try to reconcile these 2 things. Right now, I'm focusing on the role of the gas from the intergalactic medium, and then I plan to investigate how this gas is being efficiently transformed into stars. So right now, I'm using the normal sample from the first data release of Wallaby. This is we have selected 20 galaxies in the local void. So we can see here in the direction of the normal region. And I have to make a disclaimer here. We have galaxies that are a bit more massive than simply dwarfs, because we selected all of it. The sample is really small. And right now we are looking for this evidence of gas accretion. So extended H1 disks and kinematic anomalies. And I'm going to talk a little bit about how hard it is to do that. Up till now, we have found a little bit of what we expected to find. So we have disks, which are very common in voids and in the field, as we know. And we also have found galaxies that have no optical counterpart. And this one here is a good example of the kind of trouble we are facing, because most of our sample is very close to the galactic plane. So it's very common to have these really crowded fields, and you basically can't see anything. And we also found what we were looking for. So we have these evidences of, oh, I'm sorry about the noise. We have evidence of warps, offset H1s, things that are showing that these galaxies are going through some type of evolution that is not straightly what we expected. So there is something happening there. But mostly these galaxies are unresolved, as we can see in this offset H1 here, and thus making kinematic models. With these data, it's not possible for these objects right now. But I want to focus on another object that we found in our sample, which I think is one of the most interesting ones, which is the system known as Catherine's Wheel. It contains the nearest collisional ring known, and is comprised of 3 low-mass galaxies, so galaxy A, B, and C. And it is believed that this ring formed when galaxy B went through galaxy A. So it has not been much studied since it was discovered, because it's very close to the galactic plane. However, Wallaby observed it, so we went to see what do the H1 observations with these spatial resolution tell us. So first, we did the moment map. So I'm showing here that we can see there is a very large envelope of H1 surrounding the system. The red arrows indicate the location of the 3 galaxies. And the thing that stood out the most is that the peak of H1 emission doesn't belong to any of the galaxies. And it also has a high velocity and high velocity dispersion as well. So this led us to think that maybe there is a 4th galaxy in the system. And when, after thinking that and checking other observations of the system, we can see that there is a star formation, evidence of a star formation in this region as well. So what I did up until now is to estimate the star formation rates and the stellar masses, basically using WISE observations and IMU, which is something that we plan to do for other galaxies as long as IMU observations are being released. And unfortunately, I can tell you a lot about the H1 content of each one of these objects because the beam from Wallaby is not enough to resolve the inner parts of the disk from the individual galaxies. So we are trying to get high resolution data for this system. But what I can show you here, and especially if you look at the middle row for the system of these channel maps, we can see that it's very messy. Like you can really resolve anything inside the ring. So we tried our best by doing kinematic analysis to maybe trying to see how much it deviates from a disk because there is a very clear velocity gradient. And we see the expected residuals for galaxy B and for the unknown object. But we also see this residual, there is like a faint plume. And this is pointing to maybe the history of interaction between the galaxies in this system being more complex than we thought. And last but not least, we also, when we look at the velocity here, the residuals also are big for the region, the unknown object. And even though the position velocity diagram doesn't really pass through that one, we can see that there is like a faint tail between 1,000 and 550 kilometers per second, which is this unknown object. So we are trying to get more high resolution data to really figure out what is happening in this system. So this is very much still a work in progress. And I want to close this by talking a little bit more about the next steps that I'm going to take. So as all astronomical work, I think more data, more galaxies, and more analysis. We are trying to get applying for observation, but we are also expecting data that has also already been observed with Wallaby. And there's also data from IMU that we are excited to dig into. Try to use optical photometry whenever possible, but it's really difficult for the sample. And also do a hydrodynamical modeling of the system to understand how it did actually form, having these H1 information. So if any of you know how to do that, please talk to me. And in summary, we are investigating these low mass systems in low density environments, trying to understand the role of gas accretion, and we really expect to expand on it and have more things to show in the future. And that's it.
All right, there's time for a couple questions. Do we have any online yet? Not so far. What about in the room? Ah, okay. There's one up there first, yeah.
Thank you for your talk. I was wondering about the last PV that you were showing. I think it was in the approaching side, there was a part that is not reproduced by the model, right? So this minus 100 arc seconds, minus 100 kilometers per second.
Mm-hmm.
I was wondering if you checked in the channel maps, where is that emission coming from? It's not super clear from the
Yeah,
list.
this emission is actually the one that we associate with the bullet galaxy. So it's actually pretty weird when you think about how here we have basically the bullet, and here we have the weird object that appeared in H1, but it has like a clear gradient. But yeah, it's associated with Galaxy B.
Okay, thank you.
Session.
Very nice. So this is Betsy Adams, Astron and chair of the symposium. Very cool. So first, just super cool that there's this giant H1 disk that all these galaxies are embedded in that you're working on.
Mm-hmm.
But like for the question, you seem to be really struggling with this high galactic extinction. It just makes your life hard. So where would you like Wallaby to next observe its high priority fields where you have voids but less galaxy? Can you tell them that some of them are in the room? Maybe they'll listen.
Yeah, I hope they do, please.
All right. Well, I think that's all we have time for questions. Let's thank Asa one more time.
Thank you.
And that puts us on the final talk of this symposium, the conference summary by Thijs van der Holst. Go ahead, Thijs.
Yes. Thank the organizers for asking me. At least that's what I thought before I started this exercise. Now I'm not sure whether I should thank the organizers because it's a hell of a job. And I basically had to really make a very fine selection, but I'll try to, as much as I can, give my impressions of the conference and give a little bit of a forward look, because in the 20 minutes that is left, that's really, really difficult. But to put things in perspective, this is a timeline for when the first H1 observations, resolved H1 observations of galaxies started, back when the Westerbork telescope was constructed in the late 70s and became operational in 69. The Cambridge half mile had done M33 and a few other galaxies, but not really as many as Westerbork did in the following 10 years after its construction. And of course, later we had the VLA, the compact array, in the late 90s, the GMRT, and then actually, as a result of the SKA project starting in the late 90s, ASCAP, CAT7, and eventually MEERTCAP, which we are now basically using and see fabulous data from, were realized to get sort of prepared for the SKA era. The same is true for FAST, although FAST is built on one of the original proposed SKA sites. It was not selected as a site, but it resulted in a fabulous telescope, which we have heard much about. Now, to put myself in this timeline, for those of you who don't know me very well, I did my thesis with early Westerbork data, and the main object in my thesis is M81 and NGC 3077, and especially the H1 in between. So that was sort of the first view in H1 of interacting galaxies. And my roommate, Albert Bosma, worked on a number of galaxies and made this great discovery that the rotation curves not only extend because you're using the H1 rather than optical measurements of rotation far beyond the optical disk, but are flat. And that basically was the birth of dark matter, although he is not really always recognized as having the best evidence for dark matter. And then I went to the VLA as a postdoc, or to Socorro as a postdoc. I started using the VLA, which was not a line system yet. That was in the late 70s, early 80s. But I did observe M51, and that picture was shown by Ying, and I'll show you the other picture with the fast data included, showing you all the gas around it in a moment. ATCA produced many results, and I just saw as an example M83. And in the sort of late 90s, that was the era when I personally was involved in finding high-velocity gas in galaxies, together with Renzo Sansisi and a number of other people, first in M101, and later, because in an edge-on galaxy, of course, you can see whether things are above the disk or not, and 81. And roughly in that same era, Frank Briggs was putting together the first H1 mass function from our Arecibo data. And of course, now we use H1 mass functions from all the data we have been getting, and I will skip the high pass and the Arecibo and alfalfa result just for a matter of time. It's hard to be really complete. Now, after the turn of the century, a lot of data came, a lot of projects started, like, for example, THINGS. We have seen some of those results, and the realization that actually you need more than just the H1, and also other data, spectra, other lines, like the CO line, ionized gas information, star formation information from optical broadband photometry, and so on. So the multi-wavelength aspect became very clear and very ingrained in trying to understand not the H1 and also the kinematics in terms of the evolution process in galaxies. And it's also in that time that we saw the first sort of beautiful pictures of the Virgo cluster, where the galaxies in the inner parts are really small and stripped, with the first evidence for RAM pressure stripping. And the first, when people were pushing for sensitivity, the first small galaxies were found, and this is one example, Leo T. And then these SKA precursors and SKA induced telescopes like ESCAP and MEERKAT and FAST produced many of the marvelous results that we have seen at this conference. And here are just grabbed a few pictures. In blue, you see M51 plus FAST. Compare it with the other blue picture there, and that's what I'll talk about a little more in a moment. Well, as I already said, it's impossible to cover everything. 49 talks and over 100 posters. I downloaded all the posters and very quickly went through it, but I gave up. It's just too much. So my apology to all the people who made definitely marvelous posters there, to all those people who I cannot sort of mention and present their work. So I'll restrict myself a bit to a few highlights that I picked up personally. There's a wide range of topics covered. It's not just H1 in galaxies, but it also many aspects, various environments, galaxy clusters, galaxy groups, but also aspects like H1 intensity mapping and epoch of reionization. And the various ways to measure cosmology. For example, Matthew talked about the cosmic flow fields. The reviews, I think, were all very well done. I'd like to really compliment all the review speakers because they gave a very good overview of what they were asked to review, which for me was very informative, but I hope was also informative for many of the young people, because one thing that struck me, not just at this meeting, but at this entire IAU, is how many young people there are, which I think is extremely encouraging, because they will use SKA, I won't. So let me now just a few thoughts and comments. I already mentioned the multi-wavelengths aspect of really required to understand galaxy evolution. And that was first mentioned by Michelle in her review. And I think that the three reviews we had at the beginning were an excellent start for the whole meeting, and also for other people who may not attend this meeting to get an overview of what we are all worrying about. Surprises, I have a few. I'm really puzzled by this result that Erwin de Blok presented. These are two galaxies from the Mongoose survey, and of course Mongoose is doing galaxies like WISP and THINGS and Little Things did, but the advantage is it goes a lot deeper. because it's a very sensitive system, but also the field of view is wider. And that means that in one shot you do not just get your galaxy, but also a large part of its environment, of course, depending on how distant the galaxy is. And what struck me here is that the one galaxy at the left sort of looks like what I expect, and the one at the right I'm really surprised about. There's only one little companion there, and for the rest of the galaxy is sitting there, has steep edges, which in the past people ascribed to evaporation of the edge of the H1 disk. So this needs to be resolved and addressed, and I'm sure the Mongoose people will do that. And of course, the wide field of view, it gets even wider if you use ASCAP, because you have the phased array feeds that give you a large field of view, but also many pointings with Meerkat. Is a wealth of information that the groups that are working with it are now only beginning to digest on the various morphologies of the galaxies in those groups. To the left, the Fornax cluster, and to the right, the Eridanus group. But we got some good overview of scaling relations, of course, by Luca and Martin. Scaling relations, of course, have been used with the single disk surveys of H1 in galaxies High Pass and Alfalfa and follow-up observations. And they are basically a statistical approach, because these galaxies are not resolved. All you have is a H1 mass and a velocity width, and you have to work with that. And you can already see in this diagram that I think Luca showed that the scaling relations are clearly there, but there's a lot of scatter. And if you plot other parameters here now in color, that definitely perpendicular to the relations, there is a spread. A scatter is another physical parameter involved, and maybe several. So eventually, I think we need to have all these parameters and then look at the multidimensional data to make sense of what is ongoing, and isolate the various objects in the multidimensional space. There's one thing to worry about. It's the systematic effects, and there are many, and some of them have been mentioned. And I was really sort of, on the one hand, pleased to see, but also brings home that you should be very careful not to compare apples and oranges. This is a plot that Tobias Westmeyer showed in his ASCAP overview, where if you restrict your H1 measurement to the optical disk and then measure an H1 fraction and plot that as a function of surface density, you get a much narrower relation than when you take the total H1, which of course also includes H1, which is outside the star-forming disk. So we have to be very careful about how we use the various parameters. And a project like Dingo, this is well, to me, fascinating view of what Dingo will produce that Martin gave us, with all these galaxies that all have the things that we can measure, and eventually, because many of these will not be sufficiently resolved, studying these scaling relations. So we definitely need the optical data as well. Well, I thought it's good to see, and slowly things begin to converge a little bit, but there's still a lot of work to do, and also there the systematics is an important issue, is to push the scaling relations toward higher redshifts, mostly through stacking, but the stacking results now seem to give the right dependencies, and in general the trend seems to be that in the early universe the galaxies are H1 richer than they are at the present day, which sort of fits with the things Céline told us this morning. Environment is of course important, has always been sort of a mantra, look at the environment, but how do you do that? And people do it different ways. People use friend of friends. People use disperse to look at where things are with respect to the cosmic web. And of course, they're all good. The friends of friends is more local. The cosmic web is more the general background of mass distribution in the environment of the galaxies. But we have to be careful. I think we have to do all of it to see what really drives the processes that we are studying. And one thing that wasn't mentioned, unless I missed it, there's an interesting paper by Aragon Calvo, Joe Schelke, and Mark Nijrink, where they look at the cosmic web and actually have a model for the effect on galaxies by just moving through the cosmic web, but also taking into account the flows of the cosmic web. And I think that's an important thing as well. It's complicated to do, and you need redshift surveys of lots of galaxies, bringing back also another aspect why redshifts are important, to map the velocity field. So there is a lot of work to be done, but I think it's worthwhile to look at that. Now, the state of affairs in the galaxy, to actually already mentioned that you need all the additional information. One thing that came up was the symmetries, and I'd like to say 2 words about the symmetries. Is this a good indicator, yes or no? The indicators come from the optical, of course, and the one that is apparently probably the most robust is the modified symmetry. This is basically rotation symmetry, as has been shown by Nadine Giese. And if you look at mock galaxies, then the plot to the left, shows this for different resolutions and different column density thresholds. What is plotted is horizontally the asymmetry measured in the noise-free case, and on the vertical axis when you start adding noise. The other thing is, if you have only a global profile, the only asymmetry you can measure, and that is shown in the top right, is the asymmetry in a global profile. And we heard a talk about that. And that, of course, is a very convoluted measurement of both velocity asymmetries and spatial asymmetries. So Pooja Bilimoga looked, and this will be published, I hope, soon, at this for her thesis, and compared the 2 measurements, the spatial asymmetry and the global profile asymmetry. And the top at the bottom shows one plotted against the other, and there's not much of a correlation, except when things are extremely asymmetric. So that's something to keep in mind. It was also good to see that actually from models that the asymmetry parameter, rather than the Gini and the smoothness parameter, are a good measure, better than Gini and smoothness. Now finally, to disentangle these physical processes, I think it's extremely important to look at the 3D structure. And this was shown in this example in the Fornax cluster, where the velocity structure is used to sort of try to disentangle ram pressure stripping from tidal effects. And I think it's important to look at the complete 3D coherence, especially for complicated objects in 3 dimensions, not just by going channel to channel, but actually my conviction is that you should look at the 3D data. So the VR that is demonstrated at this conference, IDAV, is a great tool to do that. Well, we heard a lot about the Milky Way, and of course, the nice thing about the Milky Way is we have very fine information about the structure, but also because there's both absorption and emission, one can now really make a good attempt to get to the physics and the temperature distribution and the pressure distribution in the interstellar medium. And I find that fascinating that the era is now there to do that. In the end, we have to connect everything we do in the galaxy and the nearby galaxies to the outer universe. And so at some point, we have to sort of take the nearby galaxies and take them, basically look at them less and less resolved to see what they would look like at higher redshift. And Celine showed this morning that a lot of the material there is neutral gas, so somehow we should have the ability to also the high redshift to get to things. Again, systematics are important. This morning, Julia Bluebird showed from the Chile survey these very high redshift or high redshift detections. But the stars are from stacking. Nick Luber talked about that. The dots are from direct detections, and there is a difference that needs to be resolved. But maybe it is a selection effect because detections only picks out the brightest galaxies. Well, those were just a few things that struck me. There's many more things, and maybe we should actually go not just home, but keep in touch with each other and keep talking about these things, because I think it's very important. We have lots and lots of data we're all working on, and it's beautiful data. I wish I had more time than the 24 hours in a day, minus the 8 that I need to sleep, to work on these things. There's a lot of science to be done, and for a while we do not really need the SKA. although it will be constructed and we're all keen to use it, but we have lots of things on our hands. And so consider what you're doing as basically preparation for the SKA. And to the SKA office, I would like to say, I'm not sure whether they are listening or in the audience, talk to the users more than you do. Because there's a lot of experience out there, you should use it when you construct the VLA, not the hardware, but especially everything you need to do the science. So prepare for the deluge of data. And I should end here. Enjoy working with all the good data that we have seen this week. Take home what you learned and keep in touch. Thank you.
We have time for a couple questions, if there are any, or additional final thoughts would also be an option.
Christine.
Perhaps we could have a big round of applause for the organizers of the conference, and in particular Betsy, who has kept us on the straight and narrow for 3 excellent days. Thank you very much.
Absolutely. Thank you, Christine, for reminding all of us.
Any other questions or comments? Then I believe I hand this mic over to Betsy.
Yes. Okay. Well, first I want to take a picture, but I'm not like fancy enough to manage to get a selfie while I'm up here, so it's just going to be a picture of all of you, which is actually my favorite sort of picture when I'm not in it. Okay. So I claimed the microphone at the end. I hope you'll all bear with me for just a few minutes more. I know it's 5. I just wanted, I have to find my notes so I don't forget, to take a moment to just say thank you all for this session. I've had an absolutely great time. My notes aren't good. There we go. And so I want to start with thanking all of our speakers, because it's just been a great program, with a special shout out to Tice, who was given the hardest homework task of any of our speakers. So thank all the speakers again, please. And then, of course, I thank the SOC, who are the ones who read all the abstracts and put this program together for all the great speakers. So thank you to the SOC. I want to thank all of you, all the participants. I love how interactive been. There's been great questions. Everybody being interactive on the Slack. The online participants who've been checked in and asking questions. So thank you all for making this an engaging and interactive symposium. A special shout out to the co-chairs of the symposium, Sarah, Natasha, DJ, and Anastasia, for all the behind the scene works we've done. Things like the website, putting the poster sparklers together, and maybe just as a little note to everyone, our behind the scenes work is not done yet because the proceedings will be coming, which also adds Julia and Moses as editors. So don't forget that you have that to do. And so then thank you to the co-chairs. The great thing about organizing a meeting here at the GA is that there was a whole lot of work that I did not have to do, or we did not have to do, because of the knock. So I doubt any of them are here, but we should still appreciate them. And then I want to end with a giant shout out to our technical team. I feel like we've had a great experience here. I think it's been a good experience online. They've been so super supportive and awesome. So big shout out to the back of the room. Okay, and that's it. I wanted to keep it short. It's 5. Oh wait, I promised Natasha she could steal the mic from me.
Sorry, I just wanted to echo what Christine said. Just to take the opportunity to thank Betsy for being the chair of this symposium. She's done such an amazing job. She's done a lot of heavy lifting, and I think her organization skills really show through with how smoothly this went. There were no issues. You've answered a lot of emails and done a lot of work with a lot of composure and a lot of intelligence. And so I think we can all just thank Betsy again for such a good symposium.